Good morning, everyone. Welcome to Sci-Tech Spins, where IIT Delhi professors engaged in cutting-edge research in science, technology, and allied fields are delivering lectures and conducting laboratory demonstrations, taking students on short but riveting spins into the fascinating world that surrounds us and that still holds innumerable mysteries for us to resolve. This is the second part of the Unraveling Nature series. In the last one, we had gone through our universe at large scales. Now it's time to plunge into the microscopics, which will be in two sub-portions. So look out for an intermission in between. Our first speaker is Professor Tarun Sharma. He did his doctorate at Tata Institute of Fundamental Research, Mumbai, and he has held several postdoctoral positions abroad before joining the Department of Physics at IIT Delhi. His research interests include quantum gravity from the perspective of string theory, hydrodynamics, and fluid gravity correspondence. So he'll be talking to us first, and we'll be having an intermission in between. Tarun, over to you.
Okay, cool. So, hello, everyone. So today, in our second part of this, exploring the universe theme from last time. This time, we will take a journey into the subatomic and the world of particle physics. Okay, and try to figure out what are the fundamental building blocks of our universe as we go into smaller and smaller scales. So what I'm going to do is to take you on a sort of historical journey into the discovery of subatomic world. Okay, and as we move from this terrestrial world where we see and understand physics to a great extent. Okay, how do we figure? How did we figure out over time as to that the laws of this terrestrial mechanics have to change, and a new set of laws are to be discovered which rule the quantum world, rule the subatomic world. Okay, so I'll take you on a historical journey. Let me. Okay, so let's start. Okay, good. So now, one of the fundamental questions that everyone, as a kid or, as just human beings, we are very curious about, okay, is, when we see all the stuff that is made around us, we see a wide variety of different kind of stuff. And we wonder whether all of this stuff is, made up of some fundamental building blocks, which are individual, which are different for each of these individual things, okay? Or is there some sort of universal structure, okay, to to the things that we see around ourselves. Okay, so this is one of the basic human endeavors that human beings have always wondered about. Okay, now again, to start at some finite point back in the history. Okay, the first one to give sort of concrete answer was John Dalton. Okay, his he gave a classification of all the different kind of stuff. Of course, building on the work of many people before him and his colleagues together. Were okay. He gave us a general classification. Okay, of the stuff that we see around ourselves. Okay, so he divided all the stuff that we see around into two general class of things. One of them he referred to as elements, okay, and other ones as compounds. Elements have had this property that they seem to be made of same basic unit. Okay, that if you try to break them down further and further and further, okay, it seemed like that the fundamental building block of them was from one particular kind of basic fundamental unit. Okay, which of course varied from element to element. Okay, and then there were things which classified as compounds. Okay, which had this feature that they look like that they are made up of by mixing these elements. Okay, which have only one kind of fundamental basic building block unit. Okay, when they are mixed into each other in very specific proportions. Okay, then they make up new objects, and these objects which are made together by joining or combining elements, Okay? They were referred to as compounds. Okay, so the basic unit of elements, okay, elements which seem to be made of only one kind of things. Okay, these elements, these basic units which constitute elements, okay, they were referred to as atoms. The idea that everything is made up of some sort of fundamental building block has been around for many hundred years, okay, in various civilizations, okay. um, but identifying them as units of some part of these uh, objects called elements, okay, this classification, under this classification of John Dalton, okay, these things called elements, okay, their building blocks were referred to as element. Compounds were made up of mixing different kind of elements together into, okay. This word atom came from this Greek word known as atomos, okay, which meant indivisible. Okay, so this was again a natural thing to see. Imagine that there is some sort of indivisible. If you keep trying to break up matter into smaller and smaller and smaller pieces, okay, then at some point you wouldn't be able to divide it any further, and then whatever is the fundamental building block, which cannot be divided further, okay, would be just called as an atom, okay, and everything would be made up of some atoms like this, okay. But fortunately for us, if that were the case, that everything was just made up of a different kind of atom, okay, this talk basically would be over now, okay, and there wouldn't be much to say apart from just trying to figure out properties of all these individual atoms of different objects, okay. So fortunately for us, it turned out that fortunately for us in science in general, okay, it turned out that atom was probably just like a wrong choice of name, because it turned out that atoms were not really indivisible, okay. The fundamental building blocks that we think of, fundamental identical building blocks of these objects called elements, they are not really indivisible, okay. So let's go on and see how did we historically come across further structure of atom itself, okay. uh, Again, among various scientists who worked on these problems, okay, John Dalton was one of the leading figures, okay, who studied these things called luminous rays, which are emitted when you connect when you when you connect a negatively when you take a negatively charged electrode, okay, and then increase its potential difference from a corresponding positively charged cathode, okay, anode, okay, keep them apart from each other, okay, and create a high potential difference between them, okay. So this is the original figure of cathode ray tube. I hope you can see my cursor moving around, okay. So this was the original figure of this cathode ray tube that Thomson and many others used to study these emissions. Okay, so what they did, so this is it's not really easy to understand what's going on. So there is a schematic figure of this which I'm showing here, which is playing here. So what is done is that there is a negative electrode, and then there is a positive electrode which creates a positive potential difference onto a plate. Okay, now when you create sufficient vacuum, okay, sufficient vacuum inside this tube, okay, and then create high enough potential difference between the cathode and the anode, okay, then the cathode seemed to emit some sort of luminous rays, okay, and these rays were called as cathode rays just because they were emitted from the electrode which was called cathode, okay. So he observed these luminous rays, and many people have observed this. John wasn't the first one to observe these, okay, but he systematically studied their properties, okay, by looking at what do these what do these luminous rays, what kind of properties do they carry. So you go and measure things by doing experiments, okay. Now, what he did was to study the effect of electric and magnetic field when applied to these luminous rays. Okay, and then just by studying them, as the figure shows, okay, you could apply some sort of electric field across these rays which are traveling here. Okay, and then depending on which direction do you apply the electric field in, okay, or the potential difference, these got deflected. Okay, these got deflected in the direction of the positive in the direction opposite to the electric field. Okay, so this showed him that that these things they have some sort of negative charge associated to them. Okay, and then he also studied the effect of magnetic field on these cathode rays. Okay, and then using the fact that these charged particles, whatever these charged objects are, these rays, okay, which are coming out of the cathode, they carry electric charge, and they are deflected by electric and magnetic fields. Okay, so studying the effect of electric and magnetic field on these things, okay, he figured out the charge to mass ratio of these corresponding particles which were making up these cathode rays. Okay, so these these particles, they carried some charge and they had some sort of mass associated to them. He studied them and then concluded the following things out of this, out of the experiment that he did with these cathode rays by measuring this charge to mass ratio. Okay, it turned out that regardless of what material do you use for cathode, okay, for the electrode which is emitting them, okay, it was the charge to mass ratio seemed to be completely independent of which material do you use for cathode. Okay, so it seemed like that every different material that you could use, they all emit the same kind of particles. Okay, because the charge to mass ratio was same for everything. Okay, and then the determined ratio for these electric and these charge to mass ratio of these particles, he computed them, and it turned out that it was, to the accuracy that he could determine, okay, these were more than 1,000 times lower than that for hydrogen ion. Meaning, you take a hydrogen atom, okay, and then impinge some sort of radiation on that, and it gives you these hydrogen ion which carry positive charges. Okay, and for these hydrogen ions, or effectively hydrogen atoms themselves, okay, it turned out that these charged particles, they had 1,000 times lower charge to mass ratio compared to these things. So it seemed like that they are probably something which are smaller than even the lightest atom that we know of, which is the hydrogen atom itself. Okay, now Robert Millikan. Robert Millikan was another giant in this field. Okay, who discovered, who did a fantastic experiment. Okay, of trying to measure the charge of these of these of these particles which make, okay, these which make these cathode rays. Okay, so what he did is to do this famous oil drop experiment. Okay, in which what he did is to take very small oil drops. Okay, impinge them with X-rays which are coming from some sort of radioactive materials. Okay, which ionize these charge drops. Okay, and then by up and these charge drops, because they carry some mass, they would naturally fall under the effect of gravity. Okay, but then he figured out that you could apply an electric field in the opposite direction. Okay, and try to balance the weight of these oil drops with the force that electric field applies on these oil drops, on these charged oil drops. Okay, his original setup that he uh, used looked like this figure that on the left down corner. Okay, but a more schematic version of this is shown in this figure on the bottom right. Okay, so what he did is there is some sort of spray which throws oil droplets, very small oil droplets. Okay, and then he impinges them with X-rays, which are not shown in this figure. You impinge them with X-rays, which ionizes them. Okay, which produces some charge in them. Okay, and then using this plate, he allows very one by one very small number of these small oil drops through this into between two plates, which there between which there is some very strong electric field. Okay, and then by adjusting the electric field, he figured out that he could basically suspend charged oil drops mid-air. Okay, so that was because the weight of the oil drop is being balanced by the electric force that is acting on this charged oil drop. Okay, now measuring by balancing this thing, he could figure out the size of from the size of the oil drop, which he could just look at, and knowing the density of the oil, he could figure out what is the mass of this. Okay, and then the charge would easily be computed by calculating by balancing, okay, the electric force which depends on the charge okay, and the weight of the oil drop. Okay, so this way he could, for many oil drops, he determined, this charge that is carried by them. Okay, and in one of the fantastic results that came out of this study, okay, it turned out that the charge that he measured on any of the oil drops, it turned out that it was always a multiple, an integer multiple of one basic unit. Every charge that he measured was always a multiple of this specific unit of charge, okay, which he measured to be this 1.6 into 10 raised to the power minus 19 coulomb. Okay. Now, Thomson in his earlier experiment had already mentioned, already measured, okay, the charge to mass ratio. Okay, so now that Robert Millikan had measured this fundamental unit of charge, he computed what would be the corresponding mass associated, with these with these fundamental particles. Okay, now he measured the mass to be this number, which is 9.1 into 10 to the power minus 31 kilogram. Okay, now this mass is extremely small. Okay, it's of course small compared to all the terrestrial objects, but it is significantly smaller. Okay, turns out that it's actually significantly smaller, more almost 2,000 times smaller. Okay, than the mass of the hydrogen atom itself. Okay, so now we have, you see that from the measurements of Thomson, and Robert Millikan, it turned out that they have figured out that there is a particle whose charge is same. This charge that he measured for these electrons, this was the same as the charge, carried by, for example, hydrogen ions. That you take hydrogen and then you impinge them with X-rays, it generates some sort of ions, positively charged ions. Okay. Now he measured these objects, and then we see that we seem to have a particle whose charge is the same as some hydrogen ion, but whose mass is almost 2,000 times smaller than the mass of the hydrogen atom itself. Okay, so what does this mean? Okay, these newly discovered particles, okay, these electrons that they were called, okay, they were like they were the fundamental charge carriers. Okay, they were the fundamental charge carriers both in the Millikan oil drop experiment and the cathode ray tube on which Thomson worked. Okay. Uh, uh, Also later on, it was also discovered that in radioactive decays, there's one particular kind of rays which are emitted. They are called beta rays. And later on, it was figured out that these beta rays, okay, people also did Thomson-like experiments on them by studying them, under electric and magnetic field. It turned out that those beta rays were also actually electron because their charge and mass were exactly the same as these electrons. Okay. Now, comparing, as I just mentioned, the mass of these electrons turned out to be almost 2,000 times smaller than the mass of, here I'm writing proton, but you can compare it to the mass of hydrogen atom. It's the lightest known elemental atom that we knew of at that point of time. Okay, so this is extremely light. This is extremely light, much smaller than the, one of the lightest atoms that we know of, which is the hydrogen. Okay, so it meant that these electrons, whatever they are, okay, uh, we know now their mass and charge. It meant that these are things which are smaller than atoms. They are some objects which come, which possibly reside inside an atom. So there was some sort of subatomic structure. The atoms were not some fundamental objects by themselves, okay, which cannot be divided further. But electrons were something which were inside these atoms. Okay, okay. Good. So now, now that we have learned about electrons, okay, there's some very fun, simple things that you can, do with, knowing the existence of these atoms, these electrons, okay, and then the fact that they can move around very easily, and then some simple cases, for example, the electrons can be transferred from one material to another. In case of some materials, it could be transferred from one material to another by as simply as just rubbing them against each other. Okay, so using this idea, you can do very simple fun experiments at home by yourself. Okay, which is this sort of experiment. Maybe some of you have already done this. Okay, so you see, that what you can do is take like either a rubber balloon, for example, or just any dry comb, for any comb or any even plastic pen, for example. Okay, and then just rub it against dry hair or some sort of woolen object. This is cold uh, season this time. Okay, so you could just rub them against any woolen object or dry hair. Okay, and then just keep very small pieces of paper, just break paper into very small pieces. Okay, and then see that these comb or the rubber balloon rubbed against hair. Okay, it becomes charged. Okay, it becomes charged, and then it starts attracting these so this is a simple experiment that you can do at home. Okay, it starts attracting these small bits of paper. Okay. Okay. Another very simple thing that you can do is take either a PVC rod or a balloon. But for this thing you need like a slightly bigger object. Okay, so these PVC rod or a charged balloon, okay, balloon which you can rub against again either your dry hair or a woolen object. Okay, and then this can okay this can, just by rubbing this thing, it gets charged, and then it can deflect, for example, a very small um, a thin uh, stream of water as well. Okay, so this thing happens because of something called polarization, that if you have a charged object and you bring it bring it close to something which is by itself neutral, for example these papers, paper small paper pieces, they are neutral. Similarly, the water by itself is also neutral, but when you bring a charged object near them, okay, it induces polarization on them. That is, it separates out positive and negative charges inside that, and which causes attraction. Okay, so these are some simple things that you can do at home, which are based on movement of these subatomic particles, which are electrons from one object to another. Okay, so now that we know that electrons are a part of atom. Okay, now we could start imagining what does the atom then look like. Atom has electrons inside it. Okay, what else? So again, Thomson came up with like a very simple-minded model of what atoms look like, knowing from his experiment, knowing that there are these things which are negatively charged electrons. Okay, and they seem to reside inside an atom. Okay, so he came up with this this nice picture of a thing, of a idea called plum pudding model. Okay, this was that this is some sort of a this plum pudding is like a cake in which there are these small plum things which are embedded inside it. So what he imagined is that electrons are you know are embedded in a sea of positive charge. Okay, the atoms were known to be neutral by themselves. Okay, so it meant that if electrons reside inside inside the atom, then it must be that there must be something positively charged thing inside atom as well, which balances the negative charge of the electrons. Okay, so there are some bunch of electrons, and his model was that okay, why not let's imagine that this might look like that. What atom might look like is this some sort of plum pudding in which there is a spherical cloud of some positive charge. Okay, some sort of liquid which is positively charged, and then electrons are just moving inside it, inside this. Okay, so this was known as the plum pudding model because this was based on this idea from J.J. Thomson. Okay, then again, there wasn't really an experimental basis of Thomson's model, apart from the fact that electrons, lived inside the atom, and then it also has to carry some sort of positive things. Okay, but there wasn't any experimental verification of whether this plum pudding model is correct or not. Okay, then came Sir Ernest Rutherford, who performed the famous, now famous experiment known as the gold foil experiment. It was a series of experiments, not just one experiment. Okay, so what he did is to take some radioactive material, okay, which was emitting alpha particles. Okay, these alpha particles are alpha rays. They had the property that again, just by measuring their deflection from electric and magnetic field, figured out that they are particles which are whose weight was very similar to helium atom. Okay, but they carried 2 units of positive charge. Okay, So what he did is to take these alpha particles, okay, and then hit them onto, okay, hit them onto these, a very thin gold foil. So this movie that I'm showing here on the right lower corner, okay, it shows this shows this experiment. Okay, this was the original setup that he used. Okay. Okay, this is not showing clearly the radioactive object, but this is the main setup, experimental setup that he used. Okay, so let's look at this thing again. So there are these alpha rays which come out of the radioactive material, and then he takes only a very thin beam um, out of these, and then impinges them on a very thin gold foil which is sitting in between here. Okay, right. So and then hit them onto these very thin gold foil, okay, and then observed, how these alpha particles got scattered from this thin gold foil. Okay, now one of the remarkable features that came out of this experiment was the fact that, that if Thompson's plum pudding kind of model were correct, okay, then you would have expected that, there wouldn't be much deflection out of, of these alpha particles, when they hit the gold foil. Okay, if gold is was known to be an element by itself. Okay, so it was made up of some sort of atoms which contain some electrons and some some positive charge inside. Okay, inside its atom. Okay, if plum pudding model were correct, it was expected that, these alpha particles would get very lightly scattered out of these gold foil. But remarkably, it was shown, it was the result of this experiment, that most of the alpha particles went right through them, right through the gold foil, without much deflection at all. As you can see that, most that there are many dots in the, in the direction of the beam was traveling, that these are the particles which will just go straight through the thing, and there are very few particles which got, lightly deflected. Okay, and the most remarkable thing was, okay, that there were some particles, though very small in number. Okay, there were a bunch of there were a bunch of few alpha particles, okay, very few of them, which got, deflected right backwards. Okay, with very large deflection angles. They would come back to the original screen through which, um, through which these alpha particles are passing through the center. Okay, so there were very few, but strongly deflected alpha particles as well. Okay, now this could not be explained if the atom were like a plum pudding. Okay, so then based on this, Anas Rutherford gave his model, okay, which is also known as the planetary model, in which he imagined that, um, that, that there is a very small nucleus, which heavy object at the center, which he called as nucleus. Okay, which carries most of the positive charge and mass of the atom. Okay, and electrons are just orbiting, around this central heavy object. Okay, the way that planets, move around the sun. Okay, so the sun is like the very heavy nucleus. Okay, in the case of this planetary motion, of course, the force which binds them together, okay, is the gravitational force exerted by sun on all of these planets. Okay, in this case, in the case of the Rutherford's nuclear model of atom, okay, there was a central positively charged nucleus, okay, which carried most of the positive charge. Okay, most of the positive charge and most of the mass of the atom. Okay, and electrons were just simply orbiting around them. Okay, that seems like a very natural model, and this also explains, the fact that some of these alpha particles were scattered completely back. Okay, so most of the alpha particles would pass through the empty space around, around the nucleus. Okay, and those alpha particles which come very close in the direction of the nucleus, they would get very strongly deflected. But if you are a little far away from the nucleus, the deflection would be very small. Okay, it would only be electrostatic repulsion, for example. Okay, so this was the model, Rutherford's model, that most of the space inside the atom is just completely empty. Okay, there's a very small but very massive nucleus sitting at the center, which carries all the positive charge. Okay, and electrons are just orbiting around it. Okay, so this is what I just said. Okay, but now Okay, now we figure out that there is some problem with this model. Okay, and it was a big problem known from the study of electromagnetic um, radiations. Okay, of how charged particles were known to you know interact with electromagnetic radiation. Okay, and the problem was that whenever there is a charged particle, okay, which is accelerating, that is whose velocity is changing. Okay, any accelerating charged particle was known to lose energy via electromagnetic radiation. Okay, so a charged particle, either its speed is increasing, it's moving in the same direction, okay, or it's rotating. Even rotating charged particle is also accelerating, because the direction of its velocity, the direction of its velocity is changing, so it's also accelerating. So it was known that if a charged particle is rotating around some center, okay, or it's accelerating, then it would lose energy via electromagnetic radiation. Okay, so that seemed to be inconsistent with Rutherford's model. Okay, because in Rutherford's model, electrons were supposed to be just constantly um, moving around the nucleus. Okay, but okay, so this would mean that the fact that these accelerating charge particles would lose electromagnetic radiation meant that the electron, which is a charge carrying object, okay, which is moving around the nucleus, would continuously lose energy by radiating electromagnetic radiation. Okay, and as it loses energy, the size of its orbit will keep shrinking. Okay, as opposed to what happens for the planets moving around sun. Okay, they are not charged, they don't lose energy like that. Okay, but these charged particles moving around, they would lose energy, the electron would lose energy and then eventually fall into the atom. So this is a problem. This is a problem because this says that the atom, the Rutherford model of atom cannot be stable. Okay, the electron would just lose energy and then eventually fall into the into the nucleus, in the central nucleus. Okay, so but how can that be? This can't be true, because we don't see things just collapsing into nothing. So atom is whatever it is indeed stable. Okay, so where does the stability of atom comes from? Okay, so let's look at. So this was one of the problems of this. This was one of the problems of this Rutherford model, the planetary-like model, that thinking of electrons just orbiting around central nucleus. Okay, this was not explainable. Okay, within within the classical theory. Okay, the theory in which if you know the force on a charged particle, okay, you can figure out how it's moving. Okay, and then using the fact that charged particles radiate electromagnetism, it was just unavoidable that such a model of atom is not going to be stable. So within classical mechanics, there was no way to explain the stability of atom. Okay, the fact that there is a central nucleus and electrons inside an atom, okay, was established by Ernest Rutherford. But this naive picture that we have of planetary motion was not consistent because of this radiation problem. Okay, good. So now another major drawback of this picture was that even if you imagine as we know that if for example in the gravitational system that sun, earth and other planets are moving around central sun. Okay, all sort of orbits are allowed. Okay, so since these charged particles could radiate, okay, the fact that a charged particle would continuously radiate energy as it radiate energy by radiate energy into electromagnetic radiation and then slowly go into the atom. This meant that electrons could emit all sort of frequencies of the light, okay, of electromagnetic radiation. Okay, but then people were also studying, okay, the emission spectrum from all these different elements, like you take hydrogen, helium, neon, sodium. Some of these are shown here on on the figure on the right. Okay, it turned out that the light that they emit when you heat them up, they radiate light, and then the light that these elements emit, okay, they were not all sort of frequencies. They were very very discrete. Okay, it's either, for example, this part. So for example, for hydrogen, there are these 5 different lines in for example the visible spectrum. Okay, and similarly for helium, neon, all major different elements, people studied their emission spectrum, and it turned out that they are not emitting everything. Okay, they're emitting very specific frequencies. Okay, so very discrete frequencies. Okay, not everything. Okay, now this was the problem. Okay, this discreteness of the emission spectrum could not also be explained within the Rutherford model of atom. Okay, Okay, good. So now let's go back and then first review what we know about know about the classical physics through which we explain all the terrestrial things. The Newtonian physics that we learn. Okay, so the classical physics explain the world that we see around in two different kind of things. Okay, one of them are particles. Okay, these are particles. Okay, for example, the thing that you are seeing, that for example, a ball of metal, you can think of it as, approximate it as a particle. Okay, and then there were things which were waves. Okay, these are things also which also carried some sort of energy. Okay, and then they move around. They have they are generated. They are represented by some sort of oscillations. Okay, so what were the properties of these particles? Okay, the particles had the following properties. Okay, particles were labeled by some sort of mass and charge. Okay, for example, we figured out that there is these elemental atoms. They carry some sort of the atoms, they carry some sort of mass, but they were neutral. And then we later on also figured out that there are these electrons which carry some mass, but they also carry some sort of electric charge. Okay, but they have these nice properties. Okay, all these things that we see around the time, for example, a ball or a planet, or these solid objects, they have the property that they are they are at one place at a time. Okay, and they also if nothing is, no sort of force is acting on these particles, they tend to move in straight lines. Okay, as long as you don't act, and then they will just keep moving. Okay, they also have the property that you can collide these particles into each other, and then they scatter off each other. They collide, for example, billiard balls, or these metal balls just colliding with each other, as you can see. Okay, okay, and then in presence of some sort of external force, they follow these Newton's laws. Okay, waves had slightly different properties. Waves, the properties of wave are that they are represented by some sort of oscillations. For example, sound waves, or for example, the water wave that you are seeing here in this animation. Okay, is represents the motion of the surface of the water. Okay, and then this motion gets propagated. Okay, so this generates the surface wave on water. In case of electromagnetic waves, light rays, for example. Okay, this oscillation is basically of the electric and magnetic field themselves. Okay, in case of sound waves, the thing that you are hearing out of when I'm speaking. Okay, these are sound waves, and they are basically caused by compression and the rarefaction of air, um, which is between us. Okay, uh, so these are the properties that they were represented by oscillations of some sort, some object. Okay, and they had the property that they're not localized. They're not one space, one location at a time. Okay, they're spread around in space. Okay, they have this property that they don't really move around in straight lines. Okay, they can bend around corners. Okay, so for example, the fact that if you are sitting inside a room, okay, and then there's someone standing outside the room, okay, and then there is a wall between you, but there is a door which is open. If you speak, the other person can still hear you. Okay, and this is the phenomena of diffraction, that these waves, they have the property that they can bend around objects. Okay, this, of course, particles don't do this. Particles, unless they collide with something, they don't change their direction. Okay, but waves have this property that they can bend around objects without any external force acting on them. Okay, so this phenomena is known as diffraction. Okay, they also have this property that they can occupy the same place in space. Two different waves can come and be at same place at same time. Okay, they overlap with each other, and this phenomena is known as interference. This you beautifully see in this animation that you are seeing. Okay, that that there are two balls that he is the person is flapping on the surface of the water. Both of them are creating their own waves. Okay, but it's not that that these waves don't talk to each other. It's not that they just collide and then just go away in different directions. Okay, they just overlap with each other. The oscillations causing by both of these things, they overlap with each other, and then they go through each other. Okay, so this phenomena is known as interference. Okay, and their dynamics, their evolution. Okay, that's governed by, for example, in case of some sort of wave equation for electromagnetic waves, for example, the light rays. This is governed by so-called Maxwell's equation, if you are familiar with them. Okay, but now we thought that applying these all these things that we knew about the terrestrial world, it turned out that we didn't quite understand how does the atom behave? Okay, why does the atom seem to be stable? Okay, now it seems like this sort of meant that electron doesn't seem to care about the Newtonian classical physics that the rest of the stuff, that rest of the terrestrial stuff that we see around follows. Electron didn't seem to care about that. Okay, the atoms were stable, so electron must be governed by some different sort of laws. Okay, okay. So here comes then. People proposed different sort of new laws, and the ones which turned out to be correct over time were the first one proposed by Louis de Broglie, who proposed that electrons, you know electrons or the subatomic particles, they are not either particle or waves. They have both sort of properties. They behave both as well as particles, those both as particles as well as waves, so they have both kind of properties. And then using this idea, Niels Bohr came up with the idea that electron orbits, electrons which behave which have both these particle as well as wave properties, okay have quantized orbits inside an atom. Okay, so let's look at the idea proposed by Louis de Broglie in a little more detail. This was called wave-particle duality. Okay, that particles, what the way that we classify objects as waves and particles is not really useful once you go to very small objects, or objects like electrons. Okay, they seem to carry both wave and particle like properties. Okay, so electrons have both particle as well as wave properties. Okay, so when we think of the electron as a when we think of the electron as a particle, okay, we think of this as a solid point particle, and which can move with certain velocity. It carries some mass. Okay, but according to Louis de Broglie, it can also be thought of as a wave. Okay, a wave whose wavelength, okay, whose wavelength is associated with the total amount of momentum that this electron as a particle carried. Okay, so you could take the electron and then think of it as a particle moving with a certain velocity. Okay, or you could also think of this as a wave, okay, whose wavelength is related to the momentum it carries, and the wavelength associated with the with this electron wave, okay, would be h divided by p, where h is the so-called Planck's constant. It's a very, very small number. Okay, so it can also be thought of as wave. Okay, now this was a proposal. Okay, but later on people tried to see this in experiments. Okay, and then Clinton Davidson and Leston Sharma. Okay, these were two experimentalists who actually what they did is to basically take electrons emitted from, let's say, for example, a cathode ray coming out, or for example, beta rays coming out of a radioactive material, which were also electrons. Okay, and then they diffracted them from a crystalline object, okay, of a nickel crystal. Nickel is an element which has very simple structure of it at atomic arrangement. Okay, and this was known that waves, when they scatter from these periodic crystals, okay, they form they form a particular kind of pattern known as the diffraction pattern. Okay, so this was typically associated, this diffraction patterns of scattering from crystals was typically associated with waves. But Davidson and Germer were able to show that if you diffract electrons from nickel crystal, okay, then they also form the exactly same diffraction pattern. Okay, the of course corresponding wavelength associated with diffraction pattern is slightly different. Okay, but they were able to confirm in this diffraction experiment that the idea proposed by Louis de Broglie, that electrons do behave like waves, okay, is indeed correct. Okay, then comes the question of now you are telling us that that electrons which we would naively think of as waves, okay, they are sorry, electrons we think of as particles, they are waves. Okay, but they are waves of what? Okay, now here things get more drastically different from our usual classical notions that we see around in the terrestrial world. Okay, the answer came from Werner Heisenberg, who proposed that that when we think of these when we think of these electrons as some sort of wave particles, that they are neither wave nor particle, they have all sort of mixed properties. Okay, the waves associated with these wave particles, okay, are some sort of probability, waves of probability and uncertainty. Okay, these wave particles, they do not, the way that waves do not have a specific location associated to them. Okay, whereas particles do. Okay, these wave particles had these properties that, they neither had different, very specific value of, position associated to them, neither they had very specific value of, velocity or momentum associated to them. Okay, they were just, these were to be described as waves of probability distribution, probability amplitudes, which we typically represent schematically as, some sort of wave function, which we call as wave function psi. Okay, this represents some sort of probability distribution, that, there's some chance that it might, that the particle might be, the wave particle might be here, or some chance that the wave particle might be somewhere else. Okay, so this represents some sort of probability amplitude. Okay, and, the fact that these wave particles were represented by these, by these sort of probability amplitude waves by themselves, it meant that neither their position nor their momentums were certain. We didn't know anything, we didn't, not only didn't we know, okay, with these particles didn't have specific values of, position or momentum associated to them. Okay, this was characterized in a simple equation, again by Werner Heisenberg, saying that there is certain amount of uncertainty associated with a wave particle, and then there is a certain amount of uncertainty associated with its momentum. Okay, and there is a minimum, the product of these is always greater than or certain, equal to a certain number. Again, this number is very small, it's called reduced Planck constant. Okay, so now, things become very murky. We don't know, where these wave particles, wave wave particle kind of objects are. There's always uncertainty. We don't know exactly where they are. They're described by some sort of probability amplitudes. Okay, now using this wave idea, okay, using this wave idea, Niels Bohr was able to, explain some features of the stability of atom and the discrete spectra. Okay, and his claim was basically very simple, and his claim was that, electrons cannot move around in arbitrary orbits around the central nucleus. Okay, it can only move around. So thinking of electron as a wave now. Okay, so it is carrying, we are thinking of electron that it carries certain momentum, and then there is certain, certain wavelength associated with it. Okay, so only those orbits around the central nucleus were allowed in which full wavelengths of the electron wave would fit in. Okay, so for example, this orbit is allowed. Okay, here, 5 of the waves fit in exactly. In the next, in this next orbit, larger orbit, 10 of these waves fit in exactly. Okay, whereas some orbit, in which, if the electron goes around in the wave and then comes back, but it does not come back into the same phase, that the full wavelength does not fit in. Okay, then it will just destructively interfere, and then such an orbit is just not allowed. Okay, so electron could only move around in very specific orbits. Okay, which corresponding to these full wavelengths of the electron fitting into the orbits. Okay, now this explains this explained partly the stability of the atom. Okay, now that, electron cannot just continuously lose energy, because if to continuously lose energy, it would need to go into an orbit which is just, marginally smaller than that. Okay, but that orbit is just not allowed. Okay, because electron wave cannot fit into that thing. Okay, the full electron wave cannot fit into that thing. Okay, so it can jump only between these allowed orbits. Okay, so within an orbit, it's going to be stable. Okay, it will just keep rotating there. It cannot lose energy. Okay, but it can lose energy by jumping in a discretely jumping from one of the outer orbits into one of the inner orbits. Okay, and losing the amount of energy equivalent to the difference between energies of these two orbits. Okay, and this jumps, the fact that there were only discrete orbits allowed, okay, meant that electron whenever jumping from one orbit to another, one allowed orbit to another allowed orbit, would give out that much amount of energy, and these energies would be discrete. Okay, this partly explained, why do we see from this emission spectra of atoms, why do we see these discrete frequencies for different atoms. Okay, okay, now I'll try to finish quickly. Sorry. So then, next came, that these ideas, these individual ideas of, uncertainty and probability wave, and the fact that, particles, subatomic, these particles which are very small, like electrons. They shouldn't be think of just as particles, but they have sort of both wave and particle-like properties. Okay, these are individual ideas, but okay, but we need to combine this into like a workable equation. Okay, which could be used. Okay, which could be used to solve things. For example, in the way that we can just solve given external force, we could just determine how a particle moves in the in the presence of an external force. An equation like that, an equation which determines the evolution. Given a wave particle, how does it behave in time? Okay, it was done by Schrodinger equation. He gave this famous equation known as Schrodinger's equation. Okay, which describes how does this probability amplitude that was proposed by that was proposed by um, it was proposed by Werner Heisenberg. How does it evolve in time? If you tell me that there is a particle which is moving in some external potential psi, okay, how what does the wave function look like? Okay, so you solve this equation, okay, and then this gives you the probability distribution. Okay, so this was the story of quantum mechanics. That this whole set of ideas, this whole set of new ideas which seem to govern small particles like electrons and so on. Okay, this whole set of ideas and evolution was called quantum mechanics, the mechanics which describes subatomic particles which are very, very small. Okay, now another set of another set of very important ideas which came along around the same time. Okay, was related to the fact that when particle starts moving very fast. Okay, so let's look at some simple figures. Okay, in this you see that if you look at the speed at which you would naively think of a electron moving around in an electron moving around in a hydrogen atom in the innermost orbit. Okay, it moves around at an incredible speed of 10 raised to the power 6 meter per second. Okay, it's like 1 lakh meter per second. Okay, now compare this to, for example, the speed of light, the speed at which light rays move. It turns out that it's finite. Okay, light do not move at an infinite speed. It moves at a finite speed, and its speed is even significantly faster than this. It's 300 times larger than the speed of electron inside the hydrogen atom. Okay, now people did a lot of experiments, and then they figured out very, very non-trivial non-trivial fact about the speed of light. It turned out that the speed of light does not seem to care about how you measure it. That is, if you are standing at one point and then measuring the speed of light thrown by, let's say, some laser, or if you start running along with the in some particular direction, let's say you can move it very fast. Okay, then the speed of light seem to be remaining the same for everyone. Okay, regardless of their state of motion. Now this is very, very different from the way that sound waves or other waves behave. Their speed depends on the way you measure them. Okay, but the speed of light didn't seem to depend on this. Okay, now Albert Einstein came along. Okay, and then using this idea of constancy of speed of light. Okay, he formulated a theory known as special relativity. Okay, which governed objects which are moving very, very fast. Which are moving fast compared to the speed of light. Okay, their speeds are comparable to the speed of light. Now this theory predicted many, many fantastic things. Okay, but one of them, a couple of them are, for example, this mass energy equivalent, the famous mass energy equivalence, that if you have a particle which carries certain amount of mass, it's equivalent to a there is an energy associated with just that particle, not kinetic energy, just the energy associated with the mass of the particle itself. Okay, that is given by mc square, where m is the mass and c is the speed of light. Okay, it also predicted this remarkable phenomena known as, for example, time dilation, that if a clock is moving with respect to you, okay, then it would then it would appear to run slower. Okay, or similarly, if some object is moving relative to you, then its length would appear contracted. Okay, all of these predictions of spatial relativity, they were they have been confirmed experimentally in a vast majority of experiments that people have performed after that. Okay, now we know that that there are these new laws which seem to be appearing. Okay, these questions. Okay, these new laws. okay, of quantum mechanics, okay, of probability distributions describing particles and so on, and these new laws of special relativity of particles moving at very high speed, okay, how do these things combine with each other, okay? How is it how also we further know that that there, now we looked at the structure of atom. There is an electron, and then there is some sort of positive central charge nucleus sitting at the center, okay, but is there a structure to the nucleus itself or not, okay? And then if we keep probing these things further and further, okay, even if we try to go even further smaller sizes and so on, okay, how far do we keep going, how far do we keep going, and to what point will at what point will we stop? Is there a limit? Is there a limit to how small can we go, and how what are the fundamental further building blocks of nucleus, for example? So these are the questions which remain, and in the next in the next part of the talk, after a short break, Professor Abhishek Iyer will discuss some of these questions, okay, and take you on a further journey of what we know now, and what is still left to be discovered. What are the things that we don't understand? Okay, so I will stop here and invite questions from students. Anything that you have about the stuff that we have discussed till now.
Thank you so much, Tarun, for an extremely nice talk. And I guess yes, we can take some questions for a short break, and then we'll move on with the second talk. So I did have a lot. I mean, there were actually a lot of questions. Some here on WebEx and some on YouTube. So I'll be taking a few of them. And so uh, let me first actually take. So here's a question which came from. So I'll put it chronologically because this sort of started early on. So first question was by Pushkar, and this was also on YouTube. This was regarding the Millikan's oil drop experiment.
Yes.
How do the oil drops become charged?
Okay, so good question. Actually, how do the how do these oil drops become charged? To iron, to charge the electron, to charge these oil drops, okay, what Millikan did is to impinge them with these X-rays which come out of radioactive material. Okay, it was known from the study of radioactivity that there are these certain materials which seem to emit radiations by themselves. You don't have to do anything; they're just sitting there and emit different kind of radiations. Okay, these were called alpha, beta, gamma rays. Okay, gamma rays were the ones which had highest amount of energy, and they also had this property that if you use these X-rays and hit them with different kind of material, they seem to just ionize them. That is, they seem to impart charge to them. Okay, this was eventually understood as that these X-rays they knock electrons out of atoms. Okay, once the structure of atom was understood, it was turned out that these X-rays, what they do is they are electromagnetic radiation. They go they hit the electrons inside atoms, okay, and then just throw them out. So which leaves you with an atom with electron removed, which causes which makes them charged. Okay, so the Millikan he did this by using these X-rays, by impinging these X-rays with X-rays onto these oil drops.
Okay. So there are some raised hands as well. Before I pick some of you, I'll basically unmute you so that you can ask your question. But I have this was a very nice question which came on YouTube. This was asked by Vedant Lohan, and he asked, "Is there any experimental proof that an electromagnetic wave has momentum?"
Electromagnetic wave has momentum. Actually, not just simply, you know, not just simply experimental verification. Okay, experimental verification is beyond. Now the fact that electromagnetic radiations, carry electromagnetic radiations carry momentum and hence can push object. Okay, it's at the level that where people are making objects which are propelled by electromagnetic radiations. Okay, so one of the proposals, for example, for further space exploration, is to make small detectors with some sort of reflecting some sort of reflecting array around them, some sort of reflecting array of material around them. Okay, and that will be impinged by electromagnetic radiation, for example, coming from sun. If throw and take a big enough material which can receive a lot of electromagnetic radiation coming from the sun, okay, then the sun imparts a lot of the radiation coming from the sun imparts a lot of energy and then pushes it in the direction away from sun. Okay, so yeah, the, so electromagnetic radiations do carry a lot of energy. Okay, at the moment I don't remember what was the first experiment which showed this thing. Um, but
Yeah,
yeah,
I
now
mean,
it's
you
at a
can keep
technological
those
level.
silver foils, right? And then you have
Right,
these, whenever you have light hitting on them, they can start moving.
right, yeah.
Very nice.
So
Yeah.
yeah,
Okay. So then, okay, let me unmute. We have some raised hands. Um, can you? So Daksh Arya, I am going to unmute you. You can ask your question. Are you there? Yeah.
As there is no atmosphere in the space.
sorry, Dex, I couldn't hear you very well. Can you repeat your question?
Yes, sir. Sir, the my question is the how the rays of the sun travels uh, as there is no medium in the space.
Right. Okay. Yeah. So you're good. So this question assumes and sort of correctly assumes, the way that we know other waves to travel. Okay. So for example, sound waves and water surface waves, they all seem to require a medium, okay, to travel. But it turned out that electromagnetic radiations don't really need a medium. Okay. They are just, electromagnetic wave, in which electric and magnetic fields themselves are oscillating. Okay, so in this way they are very different from other waves that we see on the surface of a pond, for example, or sound waves which seem to require a medium. Okay, electromagnetic radiations do not require a medium. They are just independent electric and magnetic field oscillations which can propagate by themselves even without a medium.
And there was another question which came in the chat box. This was asked by Anshika. The question was, where do alpha particles come from in all radioactive substances? How do they form?
Right. That good question. Okay. That in the study of radioactivity, people discover that there are these materials which seem to emit all these sort of alpha, beta, gamma rays. Okay. And then you know so it's a natural question to ask, where are these alpha particles coming from. Okay. So now the you know the natural guess is that these things are coming from within inside the atoms of these elements which are radioactive. Okay. But to answer this question more precisely, you'll have to wait for the next talk by Professor Abhishek Iyer, who will discuss as to how did we eventually explore the structure of the nucleus itself. Okay, and what sort of forces and particles act inside it. Okay, that's a good question, but you'll have to just wait for the next part.
Okay. So I don't think we have time for too many questions, but there is another raised hand by Sanjana Singh. Are you there? I'm going to unmute you so that you can ask your question. Sanjana?
Yes, sir. So I wanted to ask that what exactly that probability amplitude means and what do we conclude from the Schrodinger's equation?
Right. Okay. So, again, the probability amplitude that we are talking about, okay, it's it's a new idea. It's not similar to anything else that you have seen around in the terrestrial world. Okay. What it tries, what this probability amplitude or the wave function, okay, describes is that that whatever you are trying to describe, these electrons, okay, they are some sort of um, they are some sort of they're some sort of wave particles. Okay, they are not particle like behaving that they have a specific location. Okay, but they are distributed over the space in some way. Okay, and what are the waves of? They are waves of probability amplitude, in the sense that these probability amplitude describes, what is the probability of finding the electron at a particular location. Okay, now the probability of finding the particle, is distributed all over the space. Okay, and this probability is a dynamical thing. It moves in time. Okay, the probability at one point is at, something, let's say, 0.5 at one point of time, but over time, slowly, as you would think that the wave particle moves, its probability changes at that point. Okay, so it's a wave of probability that, there is some probability distribution at one point of time, and then as the wave particle moves, okay, the probability is changed. The motion of this wave particle is described by changes in this probability distribution itself. Okay, so our overall motion, a particle like motion in this in this probability distribution would correspond that, initially the particle, was located in some region of space. Okay, and there's some non-zero probability of finding it here. It's distributed here. Then as this wave particle moves as a whole, okay, the probability here becomes zero, but it becomes non-zero here. So instead of saying that the particle is moving, as from this location to this location, it says that the particle is, we don't know where exactly it is. There is some probability distribution here. Okay, and then as the particle moves, the probability distribution changes. So yeah, it's, again, just to say, this is not similar to anything else that we have seen, but in a way, it's like the motion of a wave. Okay, that a wave is here, but as it travels, it goes here. Okay, the energy carried by the wave transfers here. Okay, but it's not located at a particular point.
Thanks so much. So one last question. I'm seeing a lot of other questions also. So we'll be stopping again after the next talk, and then there'll be considerable time to ask more questions. So I'll take one last question, and this is from Jayati. Jayati, I'm going to unmute you.
Thank you, sir. Good morning, sir.
Good morning.
Yes, sir. Sir, why spectral lines get split after passing through magnetic and electric field?
Sorry, your voice is a bit muffled. Can you repeat your question again?
Yes, sir. Why spectral lines get split after passing through magnetic or electric field?
I see. Okay, so this is something that I didn't discuss in the talk, but I imagine what you are asking is that, that if you have these, when you say spectral line, just for, other students as well, okay, that when you have, when you look at the emission spectrum of these elements, okay, what is happening that, you heat them up, they radiate some electromagnetic radiation. Okay, again, these electromagnetic radiations are of discrete frequencies. They are not some, all sort of frequencies mixed together. They're only very specific frequencies. Okay, what Jayati is asking is a known phenomena known as that, if you take these atoms which are emitting these electromagnetic radiation and then place them under electric field or magnetic field themselves, okay, then it seems to turn out that many of these, single wavelengths which were being emitted, these discrete frequencies, okay, they just split up. They open up into, two or more different frequencies, okay, of slightly different things. Now these phenomena, okay, their explanation would require, their explanation basically requires the understanding that how does the orbits of the electron change when you put the atom, okay, inside an electric field or inside a magnetic field. Okay, so the allowed, in Bohr's atom, remember that, that there are these discrete orbits in which electrons are allowed to move in. Okay, and then what happens is that, when you put the atom inside electric and magnetic field, these all of these orbits, they get modified slightly. Okay, they get modified because now there is not only the force from the nucleus, but also the force from the external electric or magnetic field that you are applying. Okay, it modifies these orbits. Okay, and all different orbits are modified in different ways. Okay, not everything is shifted by constant amount. Okay, so all of these, the radiation which comes from jumping of electron from one allowed orbit to another allowed orbit, okay, shifts when you put it in electric field because the orbits themselves get modified.
So much. So I think we can move on to, thank you, Tarun, for nice talk. And we can move on to part two. And then I think you will be available after the part two as well for more round of questions. So our next speaker is Professor Abhishek Iyer, who is a high energy physicist. He completed his doctorate at Indian Institute of Science, Bangalore, and then has been at TIFR Mumbai, INFN Napoli, and Institut de Physique in Lyon. His research interests include physics and phenomenology of subatomic particles and exploring them through experiments such as the Large Hadron Collider. So he'll be illuminating further about the world of subatomic particles. Abhishek, over to you.
So let me repeat, I'd like to thank Tarun for the really nice talk and literally laying the foundation for what I will be speaking on for the rest of my talk. Now, I chose to begin with this particular picture, which you see on your screens, right? Now, why did I choose this picture? I chose this picture because it represents a very important point in the development of our understanding of particle physics, right? So this picture is from 2012. And it is due to the CMS experiment at the Large Hadron Collider. Okay, what does this picture represent? So what you see on this picture is a cylindrical-like shape, and what is happening is the following: we have two protons coming in traveling in opposite directions at nearly the speed of light, and they are colliding at the point where you see my cursor. Okay, and when they collide, they produce many particles, thousands and lakhs of them. Out of those particles, sometimes a Higgs boson is produced. And what is happening to this Higgs boson is that it's converting into a pair of photons. Now, these photons are shown by these green lines. And the fact that we saw these two photons, we could say it with certainty that there is a Higgs-like particle which is present in nature, and this historic event corresponded to the discovery of the Higgs boson. Now, if you don't understand any of the words, don't worry. I will explain each and everything which I mentioned now in detail. So this, as I said, this event was a historical event in the development of our understanding of particle physics. And in this talk, I will go through the developments which led to this particular event, and then discuss what lies ahead in the future for us and what is left to be explored and so on. Okay, so as a result, while going through this development in particle physics, we will go through the building blocks of nature, the things which we see around us, what are the most fundamental building blocks of nature. Hence, I have titled my talk in the way you see on the screen. Okay, now, in order to present my talk, I chose to say it in the form of a story. Okay, I'm saying it's a story because it's very important to get a historical perspective, just like Professor Tarun did it in his presentation. He went through the historical aspects of our understanding, starting from classical mechanics to quantum mechanics. So I will do it in a similar way. And my story will start in the early 20th century, right? It's around the time 1910 or 1920. Okay, so let's begin. What was so special about that period? So as Tarun already said, around the period 1910 or 1920, we roughly had a picture of the structure of an atom, right? And what you see on your screen is the most simplest atom. It's a hydrogen atom, right? It's a cartoon of a hydrogen atom. The red circle, you of course know, it's the nucleus, right? Of course, you can always ask the question, since we are looking for the fundamental building blocks of nature, an obvious question to ask is this: what am I made of? Of course, the nucleus is asking this question, what am I made of, right? So this answer was given by Rutherford, as you have already seen in the talk by Tarun. And Rutherford, through a series of experiments between 1908 and 1920, he said that the nucleus of the hydrogen atom is a just single charged particle called as a proton. Now, the proton has an electric charge equal to 1. And as was already discussed, for the hydrogen atom, you have the central nucleus and you have the electrons which are going around the nucleus of the hydrogen atom. Now, this proton is present in the nucleus of every atom which we know. Now, depending on the atom, it may have different number of protons, right? Okay, but now that we have answered what is there inside the nucleus of the hydrogen atom, of course, the electron has the same question. What about me? What am I made of, right? But this question, I'm going to delay it for now. Let's not focus yet on the electron, on what is the electron made up of. Let's go a bit deeper into the structure of the nucleus. Okay, now for a long time around that period, people thought that the electrons were inside the nucleus. And why is that? Why did people have this particular thought? So to understand why people thought the way they did, what you see here is actually a nucleus, right? It's a nucleus of a generic atom. Now you see two different colored balls. One is blue and one is red, right? The blue ones correspond to the protons, right? The red one, I will not tell you yet what they are. So we will just assume that the nucleus is made up of some blue colored balls, which are the protons, and something red, which we will determine in the next couple of minutes. Okay. So what was happening was there was a peculiar phenomena called as beta decay. Now, beta decay are just highly energetic electrons or positrons, right? So what was happening was in this beta decay, when people observed, there was an electron which was flying off from the nucleus of certain atoms. Now, because this was happening, people thought maybe these red colored balls are actually the electrons, right? But then, as you saw in the previous talk, and due to people like Heisenberg, his picture was already shown in the previous talk, and people like Oscar Klein and Enrico Fermi, they said, no, it's not possible for a proton and an electron to stay together inside a nucleus. So that means these red colored circles are not electrons. So what are they? It was later proposed this new red colored particle inside the nucleus is a neutron, right? This was around the period 1930s, right? So let's look at this expression again. So what is basically happening in a beta decay is that you have a certain nucleus which is going to another nucleus, right? And this can be understood in the form of a red colored ball, which is now a neutron, is getting converted into a proton, which is positively charged, and it is giving out an electron. So let me repeat. So we have a certain nucleus which has a certain number of protons and neutrons, and one neutron is basically getting converted into a proton and an electron. And the fact that an electron is emitted from in this particular process, this process is known as beta decay. So beta is, as I said, it's a name for highly energetic electrons. I don't want to use the positrons now, but let's just consider them to be electrons. Okay. And for a historical fact, the neutron was actually observed by James Chadwick in 1932. Okay, so let me repeat, the beta decay is a neutron inside the nucleus, which is converting into a proton to create another nucleus, which is here, and then we have an electron. Okay, but there is a question here. What is the charge of the neutron, right? The electric charge. I told you, and you already know, that the charge of the proton is 0 and the charge of the electron is minus, right? As was discussed there. But how did we come to this conclusion, right? I already see a few answers now, but then when we, before we have an answer, it's also important to go through the process by which we get to the answer, right? So let's go through that process, okay? To go through that process, let us consider a simple principle which is true in nature, okay? So let us consider a ball with an electric charge equal to 5. 5 means just you can choose any number. I just chose 5 just to show an example. This is the ball. Okay. Now this ball is breaking up into 5 equal and similar sized balls, which you see here. Okay. Now the question is, what is the charge of each ball? I said it's 5 and it's breaking into 5 equal ones, and I already see an answer. You're right. It's equal to 1, right? And what is this principle called? So this principle is called the conservation of charge. So when we start with a certain amount of charge, it should always be equal to the sum of the final amounts of charge. So what you see here is we start with charge equal to 5. And I told you that it's breaking up into 5 equal balls. So that means 1 plus 1 plus 1 plus 1 should be equal to 5. And that is what is happening here. So let us apply this particular principle to determine the charge of the neutron, that is the electric charge of the neutron. So what do we have? We have the charge equal to 1 for the proton. We have the charge equal to -1 for the electron. So the only possibility which you for the charge of the neutron is that I see answers already, which is very good, is that the charge of the neutron is equal to 0. Fantastic. So now we know the charge of the neutron, and it was already discovered. So what is there? Have you understood everything about the beta decays? The answer is no. The reason is there was another mystery with this beta decays. And what is that mystery? To understand that mystery, let us try to introduce another principle. Okay. And to do that principle, I will do it with a very specific example. What is that example is the following. So as I said, so what you see on your slide is a cake. So let's assume your parents buy 10 kilograms of cake every day. So that's a lot of cake, right? And then out of that 10 kilograms, let's assume 5 kilograms are for your parents. Okay. So let's take out 5 kilograms from here. So I didn't tell you is that in this house, it's you are living with your parents. There is no one else. Okay. So that means so that means 5 kilograms is for you, right? And you are very happy because you're going to get 5 kilograms of cake and everything is for you, right? Now, what happens is every day when you weigh this cake, you always find it to be less than 5 kilograms, right? Now, that makes you sad because you're getting less than 5 kilograms. Whereas when the parents took away 5 kilos, the other 5 kilos was meant for you. So that makes you sad. And then you start wondering whether there is some kind of a magic happening such that some cake is mysteriously disappearing. But then you are a scientist. You don't believe in magic. You believe in logic, right? And then you start thinking logically, right? And then you start investigating as to what's happening, right? So then you do some investigation, you look around, and then like a scientist would do, and then you realize there is a neighborhood cat which is coming and taking one bite before you weigh your share of the cake. But this cat takes a different bite every day. It depends, the size of the bite, it depends on how hungry the cat is. I mean, some days the cat is more hungry, it'll take a bigger bite. The other days it will take it is less hungry, it takes a smaller bite, okay? So for example, what is happening here is on day 1, for example, the cat is extremely hungry. You get 1 kilo and the cat eats 4 kilos of cake. On day 2, you get 2 kilos and the cat gets 3 kilos and so on. Some days the cat is not hungry at all and you get all 5 kilos. But then you realize, but then again, there is a governing principle here, is that the 5 kilos of this cake is always there. It's just that it is being shared between you and the cat. Okay. So that leads us to this principle. The total amount of cake is constant. That is 5 kilos is always distributed between you and the cat. Just because you are not getting 5 kilos doesn't mean it's disappearing magically. It's just that the cat has taken some share of it. Now this, why did I say all this? I said all this is because this also lays the foundation for a very important principle. And that principle is simply stated by replacing cake in this line by energy, right? So you have all studied energy in some form, the conservation of energy in some form or the other. The energy is constant, it's neither created nor destroyed, right? So this, we will use exactly this principle to study what was the mysterious thing that was happening with a beta decay and how did people find a resolution for it, okay? So let's look at it, okay? Now we come back to our beta decay, to what we already know. We saw that there is a nucleus where one of the neutrons is converting into a proton to create another nucleus, and there is an electron, okay? So now, let me ask a question. So let's assume the initial energy of this particular nucleus is E1, okay? And then of this particular nucleus is E2. So you can think of this E1 as 10 kilos of cake. This E2 is the 5 kilos of cake which is taken away by your parents. And this is you. So what would you expect? How much do you think the energy of the electron would be? Can I see some answers? Okay, I see 5, but in terms of E1 and E2, how would you do it? If E1 is the same as 10, and if E2 is the same as 5, yes, 10 minus 5, but then how would you express in terms of E1 minus E2? Exactly, I see an answer already. It is E1 minus E2. Exactly, very nice. So as I said, we want to ask the question, what is the energy of the electron, right? So we apply simple conservation of energy. Very good. I see a lot of good answers. Fantastic. And energy can neither be created nor destroyed. And E1 minus E2. I also see a delta E, which is a very nice way of representing. So E1 minus E2 is what you would expect, right? And that is what people at that time expected, that when you see an electron which is coming in a beta decay, E1 minus E2 is the exact energy which an electron should have, right? But what is happening here is that there was something very strange happening, that the energy of the electron is not E1 minus E2. It is less than E1 minus E2. That is same as what was happening when you were getting less cake, right? Yes, we are coming to that. So the energy of the electron is less than E1 minus E2, right? So that was again a mystery. So people thought, is violation of energy being violated here? Is such a fundamental principle which we all grew up with? Is there something wrong with this? And to answer this, we use the same philosophy, right? Just like people investigated, they thought and tried to figure out what the answer was. They thought that maybe this energy of the electron is being shared, which was the energy which all the energy which was meant for the electron. It was probably shared with some other thing. Now, what is that thing? Is it the cat? No. In this case, it's not the cat. It is a very mysterious particle called the neutrino, right? So this one, I have shown it in the form of an alien because neutrinos are extremely mysterious, right? And this was the first theoretical proposal for this highly mysterious particle called the neutrino, right? In this case, I'm writing it as anti-neutrino, but don't worry. Don't worry about the anti word. Let's just focus on the fact that this neutrino is taking up some of the energy for the electron. So just like that 5 kilos of the cake was shared between the electron and shared between you and the cat, this E1 minus E2 energy is shared between the electron and this particular strange particle called as a neutrino. Now, what is the electric charge of the neutrino? We'll come to that. But an important point is that this neutrino was, you could use the same principle. I see some background noise somewhere. Thank you. So just like we use the conservation of charge to determine the charge of the neutron, you can see that the neutron has charge 0, proton has charge 1, Electron is charged -1. So what would you expect for the charge of the neutrino? Can I have some answers? Yes, I see one answer already. That it has to be 0 because we start with 0 charge. So +1 and -1, they are there. So this has to be 0. And this was actually proposed. So neutrino, the answer is that neutrino is chargeless. Very nice. I see many right answers. Very good. And this proposal for the neutrino came due to two people. On the left, you see Wolfgang Pauli, and on the right, you see Enrico Fermi. So Wolfgang Pauli said that just like you came up with the theory that your cake is eaten by the cat, Pauli came up with the theory that a part of the energy is taken away by the this neutrino. And Fermi wrote down a mathematical theory for this particular neutrino. So these two people, they jointly were responsible for the proposal that there is this mysterious particle called the neutrino or antineutrino, and it has to have 0 charge for the reasons that we just saw. Very nice. Okay. Now let us have a quick summary of where we were in terms of our list of elementary particles around the period of 1930. So what do we know? The list of particles as per our understanding at that time was that the elementary particles were the electron, proton, neutron, and then now we have the neutrino. The neutrino has been added to the list. Okay. So the neutrino was eventually experimentally first detected in 1956. And then after that, immediately in the period of 1930s, you had the antiparticle of the electron called as the positron. It's exactly the same as the electron. It's just that it has a plus positive charge. And then in the period 1937, there was an interesting particle called as the muon, which was detected. Now, muon is exactly the same as electron. It's just that it is heavier. Okay. So the muon is also now added to the list of elementary particles. We have the electron, we have the muon, we have the proton, and we have the neutron. Good. And this is the list we have so far. So we are in this period 1935, 1936. As Tarun already explained, the electron was discovered just around the period 1900, and then now we have the neutron, electron. This is the positron, and then we also have the muon, right? Okay, very nice. But then let's take a small diversion now, and let's just look at the properties of these particles which we just discussed. That is the electron, that is the muon, that is the neutrino, proton, or the neutron. They have a peculiar property, right? And what is that peculiar property? The peculiar property is that they have a spin. Now, if you want to imagine it classically, you can think of this particle which is going round and round, but actually this is just for our understanding. But these spins, you will not, the electrons or the muons are not actually spinning. It's just an intrinsic property. By intrinsic, I mean just like our hair is black or white or green or something like that. It is also an intrinsic property of these elementary particles. We just call it the spin because it's a very convenient name to use. Okay, and these spins cannot be any arbitrary value of the spins. You can't have any random spins happening. These spins can be either up or down. And the values, as I said, it cannot be any arbitrary or random value. It can be either +½ or -½. So this is true for all the particles which I stated so far. That is the electrons, that is the muons, that is the neutrino, the protons and the neutrons. Okay, all have either a spin half or a -½ Now, these particles which have these values of spins are called fermions. Okay, fermions, the name comes from the physicist whose picture I just showed you a couple of slides back, who put up the theory of beta decay, Enrico Fermi, right? So Fermi fermions. So because he laid down the foundation for the mathematical foundation to understand these class of particles. Now, fermions need not necessarily have just plus half or minus half. In general, they can have any spins like -3/2, -1/2, 1/2, 3/2, and so on, right? But notice an important aspect. So this kind of a pattern is known as a half integer spin. I call it half because in the numerator, you have integers. Integers are nothing but -3, -2, -1, 0, and -1, 1, and so on. But then I call it half because they are half of that spin. So that's why it's called half integer. Okay, I see a question, why not +1 or -1? I'm coming to it in the next class. So let's just focus on what we have so far. We have this category of particles called as the fermions. And in general, fermions can have -3/2, -1/2, 1/2, 3/2, and so on. I immediately saw a question, are there particles with integer spins like -1, 0, 1, and so on? The answer is yes. But where do they come? Because we just saw the particles which make up the atom, that is the neutron and the proton and the electron, are just having spins -half or +half. So where do these spins like -1, 0, 1, they come? That's a very natural question to ask. To answer that question, let us take an example. So we have our two smiling electrons, which are, let's assume they are positively charged, right? So what will happen if two positively charged electrons are coming close to each other? What happens? Any guesses? I'm sure you know. They repel. Very nice. What will happen? They repel. Exactly. Okay. Similarly, you have if you have opposite charges, they will attract. But then a natural question to ask is, they are repelling or attracting without being in contact, right? Let me draw this again. They are repelling or attracting without being in contact. So how are they knowing the presence of each other? Okay, and that is explained by the fact that they are exchanging another particle. And this particle, any guesses? Has anyone heard of it? This particle is known as the photon. Yes, it's an electromagnetic field. Absolutely. It's an electromagnetic field, and this is exchanging a photon. And what you see is, in this case, if it's a positively charged, they would repel. And it is always due to the exchange of a photon. Okay, and this photon has spin equal to 1. So now we just saw that we asked the question, do particles with spins -1, 0, 1, do they exist in nature? The answer is yes. And the first example we are seeing is the photon, which is present in our everyday lives, because we always see attraction and repulsion happening, and that is always due to the exchange of these particles called the photons. Okay, this diagram has a name, and I will come to this name a bit later on. But this is a very famous way of representing the interactions between elementary particles. Okay, so particles which have integer spins. So photons have spin only 1, but in general, you can have particles which have spins -1, 0, 1, 2, 3, and so on. And these bosons are named after after a physicist who made a very important contribution. And that physicist is S.N. Bose. The famous S.N. Bose from Calcutta. And he wrote down, just like Fermi wrote down the theory for fermions, S.N. Bose wrote down the theory for bosons. So hence the name boson is coming from here. Okay. So we now have a very peculiar classification of particles. Okay, a fermion and a boson. Okay, so the examples which we saw are examples like the electron, proton, neutron are present, and they essentially make up matter. And then you have under bosons, we saw one example, the photon, which transmits information between charged particles. Okay, now I'm going to make an assertion here. One is that fermions make up matter. Don't pay too much attention if you don't understand what's stable or unstable. Fermions make up matter. That is, the atom is made up of an electron, proton, and neutron, and they have either spin half or minus half. And transmitting information between fermions is due to bosons. Okay, so I hope it is clear now. We have the fermions, we have the bosons, and we saw the fermions make up matter, and then all the information between the fermions is due to the bosons. Very good. Okay, now at this point, there was an important development which happened, which was the quantum theory of interaction of light with matter. This was around 1940s or so on. I think my screen is 1950s. Okay, and this the theory of the interaction of light with matter is called quantum electrodynamics. Quantum means, like Tarun explained, we are trying to understand nature at the microscopic level, hence quantum physics. Electrodynamic means electromagnetic waves, right? It is basically bringing together quantum mechanics and the electromagnetic theory and how elementary particles interact. Okay, so this something which we draw. I said I will tell you a name for them. It's called as a Feynman diagram. So what you see here is these two electrons coming in. They're exchanging a photon and then they're going away. And these are known as Feynman diagrams. It's a very popular and a very convenient way of understanding interactions between elementary particles. Photons, as I told you, it transmits both electric and magnetic forces. That's why they call us an electromagnetic wave. And this theory of quantum electrodynamics, where we have quantum again because we are talking about elementary particles, and electrodynamics because we are talking about the interactions between these elementary particles due to the exchange of photons. Hence the word quantum electrodynamics. And this was the mathematical theory was laid down by Richard Feynman, Julian Schwinger, and Tomonaga around the period of Shinichiro Tomonaga around the period 1950s, right? And this was one of the first examples of the unification theory, where we are basically unifying electric and magnetic forces, a quantum theory where we are unifying electric and magnetic forces. Okay, very good. So this was the period of 1950, but there was also something much more not equally interesting was happening around that period. Was in that around that time, people were also wondering what is the force that is keeping the protons and neutrons together inside a nucleus. So there was this physicist from Japan, Hideki Yukawa, who said that they are held together just due to the exchange of some particle called as a mesons, right? And just like we saw that the two electrons or the electron positron are interacting due to the exchange of photons, Yukawa said they are interacting and they're held together by the exchange of these particles called as the mesons. And in that time, around 1950s, particles which had the same property which Yukawa had predicted, called the pions, which were discovered. Now, what you see is an example of an interaction. So what is happening here is this charged pion. Charged pion means pion is an example of a meson. It is converting into a muon and a neutrino. When I say converting, the more accurate technical word is called decaying. But I don't want to use the word decay because it may be a bit too technical. So I will just say a pion is converting into a muon and a neutrino. And we say we have detected a particle because we have seen this muon, we have seen this neutrino, and when we put both of them together, we can go back and conclude that these two particles are coming from the charged pion. Similarly, in 1947, a neutral pion, which was means a charge equal to 0, was detected due to the fact that it converted into two photons. And the fact that we saw these two photons, we concluded that it must be coming from the pion. So very nice. So this particles in a way fit the description of Yukawa, but they were considered to be elementary at that time. Okay, so people thought maybe this pi plus, this is a pi, okay, maybe this pi plus and pi 0 should be added to the list of elementary particles. Okay, so they did that. Okay, now, but there was something more interesting which happened was, in that period there was a tsunami of quote unquote elementary particles. So I'm putting it under quotes. Okay, and there you see, I said a tsunami because you start with the pion and then you have the kaons and so many others they are discovered. And then you start to wonder, is nature so complex that there are so many elementary particles? Because if we have, if the list of elementary particles just keeps adding and adding and adding, then it makes things a bit more complicated, because the way physicists understand nature is hoping it's actually very simple. You start from very simple first description, and then you take it from there. But then now we see in this period there are so many particles like the pions, and then you see this entire zoo. So this is actually was called as the particle zoo. Okay, for the reasons that you see here, it's just too many, and all of them were thought to be elementary at that time. But then there were a couple of physicists who thought that perhaps there is a better explanation. Nature is not as complicated like we think it to be. So what is that explanation? So these physicists said that all the particles which were discovered in this period, starting from the pions till this particle zoo which we just saw. Sorry, let us, I went 2 slides back. Okay. Yeah. So like the particle, so starting from here, and all these were not elementary. They were actually made up of these particles called as quarks. And these two physicists proposed something known as a quark model, right? And it was proposed by Murray Gell-Mann and George Zweig. They said everything can be explained by the fact that they are all made up of quarks. Okay, U, D, and S. So U, it's just a name. I will tell you what U stands for, D stands for, and S stands for. But the bottom line, or the broad understanding, was that they could theoretically explain the existence of the particles by the fact that they were made up, they were not elementary particles, but they were made up of these elementary particles called as quarks, U, D, and S. Now, the first question is, okay, very good. We have a theory which explains this particle zoo. But then how do we know that this is true, right? The reason why people felt had confidence in the quark model, as I said, why should we believe the quark model? The answer is, it predicted, apart from explaining the particles which were discovered at that time, it I wanted to use the word not produced, it predicted. So pardon me for that. It predicted another particle yet unseen. Okay, so the quark model explained those particles, but it also predicted another particle. And that particle was called as omega minus. And the fact that it was discovered at this laboratory called as Brookhaven led people to believe, and they were highly confident that this theory must be correct, that all these particles, the particle zoos, which was I told you about, the tsunami of particles, they are not elementary particles, but they are fundamental. They are composite, means they are made up of something else. They are made up of these particles called as quarks. Okay, good. So let us now update our understanding of elementary particles. So we started from the proton and the electron. We kept adding particles slowly to our list, and now we have this list: electrons, muons, neutrinos, quarks. Okay, and then they fell under the category of the fermions. Okay, so quarks, I must also tell you, is also a type of fermion. And then for the bosons, we have only one. And now you will also ask, what about the proton and the neutron? It turns out that the proton and the neutron are no longer elementary. They were also composed of these particles called as quarks, right? So now you see, I had left out the proton and the neutron from this list because by now we had understood that the protons and the neutrons are not elementary or fundamental particles. They are made up of these particles called as the quarks. This brings me to a question which I will ask you. You know that the proton has charge equal to 1 and a neutron has charge equal to 0. So in this figure, you see two up quarks, one down quark. And in this figure, we see two down quarks or two d quarks. Maybe I shouldn't have used the word down or up. So for the proton is made up of two u quarks and one d quark. And the neutron is made up of two d quarks and one u quark. So if I give you an example, set you an exercise, how to find the charge of each quark, of the u and the d quark. How would you do it? How would you set up the problem, right? So you know there is two u quarks and one d quark, right? And the sum of their charges should be equal to 1. Excellent. I see an answer already. 2u plus d equal to 1. Very good. Similarly, for the neutron, I have two d quarks and one u quark. Yes. So I have u, the charge of one u quark and two d quarks should be equal to 0. This can be set up by a couple of simultaneous equations which you have all studied. That let us call the charge of u to be x, and let us call the charge of d to be y. So we have this. Does everyone agree with this? 2x plus y equal to 1, x plus 2y equal to 0. And I believe almost everyone has solved these kind of equations where you are asked to determine what is the value of x, what is the value of y. If you now solve this equation, you come to the answer that the charge of the u quark is 2 by 3 and the charge of the d quark is minus 1 by 3. So it's different from what you have seen so far. We saw that the electrons or the muons had charge plus minus 1. Neutrinos have charge 0. But now suddenly I'm telling you the charge of u quark is 2 by 3 and the charge of d quark is minus 1 by 3. But that is how it is. That is nature. Okay. Good. Let us move to 1960s, 1967, right? Something really very important happened at this time. And what was that? There was something, a theory which was written down, which was the unification of electromagnetic and weak forces. I already told you about electromagnetic, the unification of electromagnetic forces, right? Which was due to Feynman, Schwinger, and Tomonaga, right? But what are these weak forces? I never told you anything about it. So your question should be, what is this weak force? You never told us. So let's find out, what are these weak forces? So as I said already, we came across electromagnetic forces are due to the exchange of photons. The question is, what are weak forces? To do that, let's go back to the example we started off with, okay? This example is beta decay. So in the beta decay, we have the neutron, which is going to a proton and an electron and a neutrino. Now what's happening here? So this, I have represented this beta decay in this particular format where neutron is going to a proton, electron, and a neutrino. Again, we have a particle with charge 0 turning into a particle with charge minus 1, 1, and 0. Now, we can think of it in a different way. If I ask you to draw a same diagram, if you remember, we drew a diagram where two electrons were coming in, going out and exchanging a photon. If we want to draw a similar diagram, what would we do? So let's say, and in order to do that, there must be, like the photon, there must be an equivalent messenger boson, right? Like the photon was a messenger boson for the attraction and repulsion. There must be a similar messenger boson in this case as well. So let's see what that is. So like we have a neutron coming in, okay, which is the initial thing. It is changing into a proton. Okay, so neutron has charge 0, proton has charge plus 1. Okay, and we also, it is giving out an electron and a neutrino. So what is the charge? So there is an intermediate boson. Like I said, we want to represent this by in the form of an exchange of an intermediate boson. Okay, so what is the charge of the messenger boson? Does anyone have an idea in this case? Someone said 0. You want to think about it again? Exactly. I see one answer. Yeah, it is the W minus boson. So it has a charge minus. Minus because you see neutron has a charge 0. It is turning into a proton which has charge 1. That means in order to conserve the charge, there has to be another boson which has a charge minus, so that minus and minus, minus and plus becomes 0. Similarly, if you see here, the W minus boson is converting into an electron and a neutrino. You know that a neutrino is chargeless. So the W minus boson, which is negative, is turning into another negative electron, which is fine. So we have perfectly obeyed the conservation of charge in this particular diagram which we see. Okay, so again, there are so this was the hypothesis, the theoretical prediction of this particle called as the W minus boson. Okay, so this was around the time 1970s. So W minus is the mediator of an interaction called the weak interaction. Okay, now similar to the W minus, there is also a W plus and a Z boson. These are just names, and all of them are mediators of weak interactions or weak forces. Okay, and the theory which put together the weak interactions and the electromagnetic interactions was called as the theory of electroweak interactions, and it was proposed by 3 physicists: Sheldon Glashow, Abdus Salam, and Steven Weinberg. I apologize, I missed a G in the spelling of Weinberg. And they wrote a theory unifying electromagnetic forces and the weak forces. And this was known as, or this is known as, the standard model of particle physics, which says that standard model because it is the model which explains the interactions of the elementary particles and how they interact with one another. What are the kind of bosons they are interacting? Okay, there was a few more things which happened. Okay, around the period 1970s to 1980s, there were a few more interesting things which happened. One was, there's another question. We learned that the quarks are forming the proton and the neutron. Of course, the obvious question is, what is holding these quarks together? They are holding this together. They held together by this particle called as gluons, right? Glue, because the gluon comes from the word glue, means it gluing the quarks together, and they are like the photon is the mediator of electromagnetic force. W plus, W minus, and Z are the mediators of weak forces. Gluons are the mediators of something called as the strong forces. And that is the reason why you can never see a quark in isolation. A quark never exists on its own. You will always see quark forming states like the proton, neutron, or mesons, or something like that. You will never see a quark on its own, like a U quark or a D quark or an S quark. It's because the gluons does not permit. They are very strongly held together. And with this, we update our understanding. What do we know so far? Is that we know electrons, we know muons, we know neutrinos, we know U, D, and S. Now let me give them a name. It's called up, down, strange. Okay. Now you will ask me why this name. It's just come from the historical reason. There's nothing a very strong physical reason for the behind the nomenclature. So it's called up, down, and strange, right? And for the bosons, now we have photons, W plus, W minus, Z, and now we have the gluon. So now we have really expanding our list of these elementary particles. But the question is, was this the end of the story? The answer is no, because in this period, 1970s to 1980s, there was another fermion which was detected, like the electron and the muon, but it was heavier than this. So you have the electron which has this mass, you have the muon which is slightly heavier, and then you have the tau. So electron, muon, and tau are very, very similar, except the fact that they don't have the same mass or the same weight, right? They have the different mass. So this third fermion is called, which was discovered, was called as the tau. And then there were 3 different types of additional types of quarks were discovered as well. They were called as charm, because I put C and then in brackets the rest of the name, because we call them commonly as C, B, and T. The second quark is B, bottom, and the third quark, which was discovered at that time, was the top. So now we have basically completed our list of elementary particles, and this is how it looks like at the moment. Okay, so this is through the entire historical journey, beginning from 1920s. Of course, this figure doesn't say everything from 1930s. It starts from 1960, but you see the many particles which were discovered. The ones you see here, these ones are not elementary. They are also made up of quarks. This period, W plus minus Z, was discovered around the 1980s, and then you have the discovery of the top. So this completes our list of elementary particles, and this is a very popular representation of the standard model of elementary particles and giving their list. So what you see is up, down, charm, strange, top, bottom. So we saw how they were found over the period of time, and there are 6 quarks. Similarly, we have electron, muon, and tau, and then we have 3 kinds of neutrinos, right? And then there are the messenger bosons. There's a gluon, there is a photon, there is a Z, there is a W, right? Now, this is how the particles are arranged. Don't worry too much about 1, 2, and 3. That is not very important. All that is important to us now is the fact that we have 6 kind of quarks, and then we have something electron, muon, tau, neutrinos are together collectively known as the leptons. It's again just a name, but we have this list, and then we have these gamma, gluon, gamma, the photon, the Z boson, and the W boson. But then there is another particle here which I never told you about. What is this H particle? Right? I never said anything about this. I just told you about the 6 quarks, these electron, muon, tau, neutrinos, and the messenger boson. Now, what is this H? Okay, this H was there theoretically for a long time. We could not see it for a long time until recently, but let's see. Let's not jump. Let's go step by step. So H is what is called as the Higgs boson. Okay, now why does it come? Now the reason why it was necessary was that when Glashow, Salam, and Weinberg wrote down the mathematical theory for the standard model of particle physics, they needed a consistent way or a consistent mechanism which would give masses to these elementary particles, right? So they introduced a mechanism which was, as I said, to get a mass. So they used a framework which was existing at that time, okay? And this framework was developed by many people, as you see here. So this framework was developed by many people, and the mechanism, it predicted a boson called as a Higgs. It was given a name later on, okay? The fact that we have this mechanism, if this mechanism is true, then it predicts this Higgs particle. That means if we are going to believe this mechanism, then we need to see the Higgs. Okay, so these are the different physicists who contributed to the development of this mechanism independently. So you see Tom Kibble, Guralnik, Hagen, Englert, Brout, and then this is Peter Higgs. So the reason why I did not have Higgs also in the same picture, because I think probably Higgs was clicking this picture or was probably away at that time. But this is the picture from the prize ceremony of the Sakurai Prize. Okay. Now, just like in the quark model, if we wanted to prove whether it's correct or not, we needed that the quark model, it predicted a particle called as omega minus. And we knew the quark model is correct only after we saw the omega minus particle, right? Similarly, if we want to prove that this mechanism is correct, we need to find this particle which this mechanism predicts, right? And that particle was the Higgs. Okay. But like I said here, just like the discovery of the omega minus proved the validity of the quark model, discovery of the Higgs boson is absolutely necessary to prove the mechanism for giving masses. And though it was theoretically predicted around the 1960s, 67, if I'm not wrong, it evaded detection for 50 years right? There were many experiments which got very, very close to seeing it. There was an experiment called the Large Electron Positron Collider in Switzerland, and then there was the Tevatron experiment in USA. And they've got very, very close to seeing it, but they just missed it, right? Till Large Hadron Collider entered the picture. Okay, and this is the picture you see is a tunnel of a part of the tunnel rather of this experiment known as the Large Hadron Collider. So what are the names? What does the name mean? Large means because it's really large. I will give you an estimate of the numbers. Why do we call it large? Hadron is because we are colliding protons. So protons are an example of hadron. So hadrons are particles which have these interactions called as strong interactions. Okay, and then collider means we are colliding the protons. Simple name. Okay, so let us see some facts about the LHC. We call it the LHC, so it's a short form for the Large Hadron Collider. So there is a circular tunnel. Okay, you saw one snapshot of the tunnel, which is 175 meters under the ground at the border of France and Switzerland. I will show you a map as to how the map of the tunnel looks like in the next slide. It's called large because it is 27 kilometers long, right? If you go walk along the tunnel, you will cover a distance of 27 kilometers, and that tunnel is 175 meters under the ground. And in this, we have the protons which are circulating, and they are made to, they are circulating at nearly the speed of light. And when they collide, they generate a shower of particles, right? Before we go on, this is how the LHC, the map of the LHC, the Large Hadron Collider looks like. It's circular, right? And the protons are going round and round. So if you see, this is, if you see follow my cursor, this is the border of France and Switzerland. Okay, so you see a part of the tunnel is in Switzerland, and the other part is in France. So this is the CERN facility. So CERN is the body which is it's a international body which governs or manages this experiment. And these dots which you see are the different experiments. This is called the CMS. This is called the Atlas, Alice, and let's see, they are doing different kind of physics. CMS and Atlas do similar physics. The reason why you have two different collaborations, so all of them are a collaboration of thousands of people who are analyzing the physics. The reason why you have two different ones doing the same thing is because you need to have an independent check. That is something very important in science. When you discover something, it needs to be independently verified by someone else, right? So that is why you have CMS and Atlas which are doing similar things, but they are very important that you have independent group of people doing the same thing and verifying the physics which one may have discovered. Okay, by the way, this is Lake Genève. And I hope if you get a chance to visit CERN, it's a fantastic place. You must go. CERN does have regular trips for students and faculty, those who want to explore the kind of science which are being done there. Okay, so what exactly is the LHC? So I'm slowly coming to the end of the talk. It's basically a big microscope, right? And can be thought of the strongest microscope in the world. Now, if you look at the strongest table microscope, it can see objects as small as, you see the number count, you can count the number of zeros, and this is it. But LHC does much better. It can see objects as small as 10 power minus 15, 10 power minus 16 meters. So you can see we are really probing nature at the elementary scale. So that is why we need a very energetic collider so that we can really probe the smallest units of smallest building blocks of nature. So that brings us to the Higgs. What happened? So the LHC started collecting data. By collecting data, I mean they collide protons, and it happens many times. And then it is necessary because the things that we are looking for happens very rarely. right? So if you want to increase your chances of finding something which happens very rarely, you keep doing it several times such that at some point you will find it. Okay. So that's what the LHC did. So it was doing it colliding protons several times again and again and again. And this is what happened. So you have these two protons coming in opposite directions. They collide. I call it boom. And it creates many particles. Okay. And out of those many particles, rarely you produce the Higgs, but you do produce it since it's there. And this Higgs is converted into two photons. As I said, we use the word decay, but it's converted into two photons. And the fact that we saw these two photons having the certain properties, we know it's actually coming from the Higgs boson. And the fact, as I told you at the beginning slide, we saw those two photons. It led to the conclusion that the Higgs boson does exist. And this was the discovery of the Higgs boson. Okay, and this was announced on the 4th of July 2012. And this brings us back to the picture we started off with, right? As I told you, the Higgs is decaying into a pair of photons. So this picture is from the 13th of May 2012. So this was a fantastic event for particle physicists all over the world and for humanity in general, that we have an underlying mechanism. I see a question about the charge of the Higgs, is that the Higgs has zero charge, right? There is a reason for that. Okay, maybe I'll ask it as a question later on. Okay, good. Now, is this the end of the story? Now, where do we stand with respect to, I mean, you would think that now that we have found the Higgs, we understand everything. The answer is no, because, and I'd like to explain that using this simple picture. All the things which we understood so far can actually be written on a piece of mug. So this is a mug which you would get at the CERN souvenir shop. So these are the equations which we have understood so far, right? And it is small enough to be actually condensed, put on as a picture on a coffee mug, right? This is all our current understanding. So we understand less than 4% of nature. So we are just beginning, I would say, in our journey. And in this journey, what are the things to look forward to in the future? Do we understand everything? The answer is a emphatic no. As I said, we understand less than 4% of the universe. Now, what are the things we don't understand? So some of these several unanswered questions are, for example, you have all heard about matter and antimatter, and you may have also seen in some form that when the matter and antimatter come together, they just collapse. But the fact that we all exist, right? We exist, we are living normally, means that matter should be slightly more than antimatter, because if they were the same, we will not exist, right? So the fact that this implies that the amount of matter we have in the universe is slightly more than antimatter, and that difference is enough to sustain life. But what is the theoretical reason which is causing this difference between matter and antimatter? Okay, that is the first question. What is the next question? Now, we saw all those list of fermions, right? So what you see on this picture are the masses. Now, if you look at the mass of the top quark, it is really high. So that high, the heaviness is represented by the length of this tower. And if you compare it with a neutrino, the mass of the neutrino is almost zero. It's very, very close to zero. So the Higgs mechanism, which we said is responsible for giving the mass, it does not explain why the top is so heavy and why the neutrino is so light, or even, for example, the electrons and the quarks, right? So there is no reason, there is no explanation for that. And that is also a mystery, why nature is so it's not democratic. Rather, it prefers a very heavy mass to the top quark and very light mass to the neutrinos or the electrons or the other ones. And then you have the B quark and the tau fermion, which have masses in between. So there is no answer yet. There are a lot of physical explanation. There are theoretical explanation, but the point is that when you have a theoretical explanation, it always needs to be verified by experiment. So there is no verification for those experimental verification for those theories as yet. Okay, so that's still a mystery. Okay, what are the questions for the future? Okay, so first is, we see 3 dimensions, X, Y, and Z, right? Are those all? Because that is what our eyes can perceive. But does that mean we don't have anything more than the 3 dimensions that our eyes can see? So in this video, you see a particle which is being produced and which is escaping into an extra dimensional world, right? So it's possible. And there are a lot of mathematical theories which predict the existence of extra dimensions, right? The next question is, we studied the unifying theories of electricity and magnetism. Then we also added weak interactions, right, to it. And then we had a common unifying theory of electromagnetic and the weak interactions together called the standard model. Now the question is, what about gravity? Because we have 4 fundamental forces. We have the strong, weak, electromagnetic, and gravity. So 3 are taken care of, strong, weak, and electromagnetic. What about gravity? And the next question is, if you remember the starting slide, I said, what is an electron made up of, right? There are possibilities to have this unifying theory, which includes gravity, as well as to explain what are these particles like the electrons or quarks made up of. So there is a theory called a string theory, which says all particles are just vibrations, different vibrational frequencies of a small, tiny string, right? So that is what is string theory. And then there is another theory called a supersymmetry, right? Which means that for every particle, a boson or a fermion, there is a much heavier super partner. So the question is nature supersymmetric? So that is again another question we don't know. We have a theory, but we still don't know yet. And these are not just the only questions. There are much more. These are just a very, very small subset of the many questions people are looking for. And that's why I said what lies ahead for us in the future. I would say almost the entire universe lies ahead for us to explore. And I would invite any one of you who are interested to take up a career in sciences, or even if you're interested in these things, take up a career in theoretical physics, because there's much to explore, and there are a lot of exciting things that lie ahead for us. Okay, so with this I shall conclude, and I would like to thank first is the students and the teachers for their active participation, because without them it would not have been possible. And also the next is the fantastic efforts of the IIT Delhi outreach team, which have done a great job introducing different areas of research to our younger colleagues, who maybe are the future scientists and will take our traditions ahead. And also, I would like to thank the co-speakers, Professor Tarun Sharma and Professor Supreet Singh, for moderating as well. And he was the speaker for part 1, as was already mentioned at the beginning. So with this, I would invite questions that you may have, and I shall conclude. Thank you.
Thank you so much, Abhishek, for an excellent and lucid introduction to the field of, or I should say, the zoo of elementary particles. So I would think if Tarun is also there, we can have a joint panel for questions. And although I saw that you answered a lot of questions that came during the chat within the talk itself, so that was excellent. So, okay, here's a question. I mean, it says, why is the LHC shape chosen to be circular?
That is a very, very good question, actually. So, so let's go back to history. Okay, so we started off with a couple of things. I'll also refer to a couple of things which Tarun mentioned. Right, the first thing is a charged particle, it radiates energy. Okay, so Tarun mentioned about the fact that when an electron is moving around, it can radiate energy. So, but the fact that quantum mechanics comes to a picture. So the first thing is, when we started off with an electron-positron like colliders, and they were linear. It's because, when a charged particle is in circular motion, they radiate energy, right? So they had to be linear so that you don't lose that energy. But then now with the LHC, but then having a linear collider, you have a limitation because you cannot accelerate them to very, very high speeds, because if you want to do it to the speeds which you want, or the energies which you want, you would have to make that length to be extremely long, and that is not feasible from the budget point of view. Okay, so now that brings us to the circular part of the LHC. Now protons, though they are charged, they are much heavier. So when they are traveling, they don't radiate as much energy, right? And when it's circular, you can keep going them round for several chakkars or several rotations till you make them collide. And the fact that you can keep going them round several times means that you could have your collider circular, and it goes around, and then you make them collide. It gives you an advantage from a budgetary point of view, though it's 27 kilometers still long, but again, you could really accelerate to really high energies which you want. So that's why we keep it circular for this.
Okay, that's good. There are a lot of questions which are coming in, so wait a minute. So let's see. What is the mass of a neutrino?
Very good question again. If you ask what is the, so this is again a mystery, right? So when the neutrinos were first proposed as a particle, and when they were first discovered, we thought their mass was 0, and that was a fantastic approximation. The fact that when we assumed their mass was 0. But there is one point which I didn't mention, was around 1990s, there was a phenomena which was observed called as neutrino oscillations, right? Which essentially means neutrino of one type is changing into a neutrino of another type. Okay, and that is only possible if a neutrino has mass. But then the fact that we see the neutrino to be traveling very, very close to the speed of light, and it is and all the calculations were perfectly consistent by choosing neutrino masses to be 0, suggests that neutrinos, though they have a non-zero mass, it's extremely tiny. And the question as to what exactly is their mass is a mystery, because we know the relative masses between the neutrinos, but we don't know what is the exact pattern, because as I said, there are 3 kinds of neutrinos, right? All of them are extremely small mass, but then what is the relative ordering of the masses is still a mystery. So if you're interested, you could take that as a research topic as well.
Yeah, absolutely. So I have another question, which is okay. Let me see. There are quite a lot of hands which are raised up. So I will unmute some of them, and let's see if we have a. So let's first go with Supriya Sundar. Are you there? I'm gonna unmute you, and you can ask your question.
Yeah, I'm Supriya of class 9th, KV Kadapa. First of all, I thank an extraordinary teaching of Abhishek sir. And I would like to ask that the Higgs element having the charge, neither it is a positive or negative charge. Can you please explain once the Higgs element?
Okay, so maybe let me go back to this particular thing. That I will actually answer in the form of a question. Okay. So I told you that the Higgs is converting into 2 photons, right? That's how we discovered the Higgs. Now, what is the mass of the electric charge of the photon?
What?
What is the electric charge of the photon is 0, right? Do you agree with me? Yes.
Yeah, Abhishek, I think, yeah.
Okay, so the fact that it is giving rise to 2 photons, so there are 2 photons which are charged 0, So 0 plus 0 is to be 0, which means that the Higgs also has an electric charge is to be 0. So the Higgs is basically a particle with charge equal to 0. Another thing which I didn't mention was it has spin equal to 0. So it is also the reason it's called a boson, because it falls into the classification of particles I mentioned called the bosons, because the bosons have spin -2, -1, 0, 1, 2, and 0 is the Higgs has a 0 spin. Does that
So
answer your
Abhishek,
question?
there's a related question on YouTube. So
Okay.
which is for how much time Higgs remains in a state without converting into two photons?
So the exact so that is again a very good question, right? So there is something called as a lifetime, okay, of a particle. So lifetime denotes how much a particle after it has produced can move before it converts or decays into a pair of photons. Now, if I remember, I don't remember the exact number for the Higgs actually, but it is in the order of less than milliseconds actually, much even probably lesser.
Yeah, but
Or
there is
maybe
some finite
microseconds. Sorry,
lifetime.
micro. Sorry, I could be wrong.
Yeah,
It could
yeah.
be. Okay, so it is extremely short. It's extremely it decays almost immediately. For our practical purposes, it's almost immediate, but it's not immediate because it has a finite time it exists and decays. But that time for which it exists is microseconds or probably lower. I forgot the exact number, but yeah.
Okay. So the next question I'm going to take from Karthik. I'm going to unmute you. You can ask your question.
Yes, sir.
Are
Thank
you
you,
there?
sir. Sir, I just want to ask a question related to gravity. Sir, gravity is as the general relativity states that it is the effect of the curvature in the space-time. And also, we say that gravitons exist, or we predicted that gravitons should exist that can be travel from higher the speed of the light. As the special, I want to just get answer from you that does they travel faster than from the light if they exist,
Okay,
or
Tarun,
as
you
the
want to
special
take that?
relativity doesn't allow anything to travel from the fast of the light? I just want to ask about
No,
this.
it's yeah,
Thank you.
yeah,
But
I'm
Tarun,
not
you want to take that?
clarified
yeah,
actually.
yeah.
Yeah.
Thanks, Karthik. Yeah.
Thanks,
Right,
Karthik.
yeah. So yeah, that's true. That you could ask the question of general relativity itself, that whether gravitational gravitons or gravitational waves do at what speed do they travel. Okay. Now, general relativity as a theory tells us that gravitational waves or gravitons, they do travel at the speed of light only. Okay, they're so no faster than speed of light. Yeah, it's same as the speed of light. The speed is the same as the speed of light.
Yeah. So then I'll unmute Anulia. Do you have a question or? Yeah. Let's see. Yeah. Okay. Yeah, please ask.
Hello, first of all, very good afternoon. I would like to ask a simple question. Like we just discussed about the speed of light. So, if speed of light is a constant and it's absolute, then how do you measure it? Has it ever been measured? And I somewhere heard that you can travel at the speed of light, and even at the speed of light, the speed of light is just the speed of light.
Yeah. So that is indeed
Yeah.
true, and the speed of light has been measured. And that's certainly true. Yeah, people have indeed measured the speed of light. One of the earliest you can like measure it terrestrially as well. Okay, the speed of light has been measured, and it's known to like very precise value. The
Yes,
speed.
yes, and
Okay.
the thing is, it has been measured in both the directions and not in
Right.
the linear direction. So
Yeah.
we don't exactly know if it is instantaneous or if it is just the 3 lakhs that we came up with.
Yeah, well, there is, okay, it's certainly perhaps a part of assumption, but the fact that we don't see asymmetry as such, we seem like everything else that we see around, okay, seems to be symmetric in every direction. So there is no reason to assume that it would be different in different directions, though it's certainly an assumption.
Yeah, or else the general relativity would just break down.
Yeah, it's based on it's based on general relativity, special relativity. They are based on constancy and the same speed of light in every direction.
So we assume a lot of things before we make predictions.
That's true. That's certainly true. But the fact that based on some assumption, when is a theory useful? A theory is useful when you make some assumption, okay,
Yeah.
but you are eventually able to predict something, okay. And predictions, when they work out correctly, then you say that theory is successful. So in that way, special relativity, general relativity, they are based on some assumptions, okay, but they predict a lot of things which have been tested experimentally. So in that way, these are good and useful theories.
Yeah, but when you try to unify general relativity with quantum mechanics, you find that you somehow are not able to put them together. That's again another problem.
That's a problem, but that's again, problems always exist. At every point in the history of science, there were always problems. But that's what we do as scientists, right? We try to solve these problems. Hopefully, you and other people, they would come, come and join us, our hands, and then, maybe solve these problems.
Definitely.
Absolutely.
And if everything is made up of waves, if everything is just oscillating waves and we detect it with our photoreceptors, let's just call them eyes, then how is it that, if I have mass somewhere, it is also a wave. If I have a table somewhere, that's again a wave that can be detected. If I have light, even that is a wave. So is there a difference between the size of it, or is it just the amplitude of it, or is it just the frequency of it that is changing to make things massful, or something that's not massful? I'm just making up words right now.
No, that's okay. One thing to distinguish from the thing that you started with is the fact that everything is a wave, but everything and you said that we detect them with this photoreceptor, which are our eyes. Okay, so everything according to quantum mechanics is a wave, but it's not everything is an electromagnetic wave. Our eyes are detectors for electromagnetic waves. Okay,
so we somehow evolved to experience the universe.
Experience electromagnetic, our eyes are detectors for one particular kind of wave. Our ears are detectors for another kind of waves, which are sound waves. Okay, so again, our eyes are detectors for electromagnetic wave, but only in a certain region of frequencies. Okay, so our eyes and all our detectors have limitations of what they can detect.
I think that's all. Thank you so much.
Yeah, thanks so much, Anlia, for your wonderful questions. I think we can we can take up some more of them. So there's another hand raised by, so many of them. It's just a lottery kind of. Okay, what about Om Mishra? I'm unmuting you. You can ask your question. Are you there, Om?
Yes, sir. Yes, sir. Thank you for giving me this opportunity to ask the question, sir. So my question was, is it possible to create atom from nothing or its subunit? Is there any way?
Are you saying creating atom from nothing?
Yes, sir. Just like generating it. Can we do that?
See, in principle, one can always argue that because you have this famous relation called E equal to mc square, I mean, energy and mass are equivalent, right? So you just, and there is also the other principle which we know is the conservation of energy, right? So in principle, you could always have an energy which is getting converted to matter. I won't say atoms. I would say matter under some specific conditions. Okay. Now, before we go into atoms, let's look at a very specific case. You know the photon, right? Like we talked about the electromagnetic radiation. Under a specific scenario, it can actually convert into an electron and a positron. Okay. That can happen only if the photon has a certain minimum energy. Okay. But when you talk about the atoms, that's a much more complicated object. right? It's very difficult to say that whether you can have an atom just popping up outside of the vacuum. I mean, that's something which I probably don't know the best way to answer, but it is possible that you can have matter due to a photon. This is a very famous example called as pair creation, where a photon with a certain minimum energy, it gets converted into an electron and positron. So of course it's not as if a photon is traveling and it's splitting up into an electron and positron. No, it is there is also a surrounding nucleus with which it interacts, and then you have an electron positron pair created. But the reason I said it is because your question, I thought I understood it as asking whether you can create atoms or matter in general from nothing. So I try to answer it in a way where you have energy. So electromagnetic radiation is a form of energy, right? So you
Yes.
have energy which is basically converting into an electron and a positron pair, which is matter. So that's where you have the application of E equal to mc square. At the same time, when certain specific conditions are satisfied, you have these creations. Yeah.
Yeah. Thanks, Abhishek,
Uh,
and thanks,
okay,
all.
sir. Thank you. Thank you.
Hope that answers your question. Yeah. So I'm gonna take. So I don't know how much time do we have. Okay, I'm gonna take one more question from Advitya. I'm gonna unmute you, and you can ask your question. Yeah.
Good afternoon, sir. Thank you for giving me opportunity to speak. So my question is, sir, we mainly have a theory that stars, some say stars are countable, some say stars are uncountable. But sir, if we think about what I feel about atmospheric refraction, we can say that stars are countable. Because sir, I feel when we look at the stars, it could be that sir, where our eyes go, we actually create the star that way. So like as you read in atmospheric refraction that the when the stars fluctuate and the position is actually seen higher than the real position. So sir, it could be that every time we see the position creates higher and higher, and that's why we see star everywhere. Could this be the point, sir?
So Preet, maybe you can take
This
that.
is okay. Yeah. So it's gone tangentially. Okay,
It got
so yeah, definitely. Yeah, I can take up that question. So you see, first of all, there is a refraction for sure, and which changes the apparent positions because the light, of course, bends as it move around. Just like you take a piece of glass of water and you insert a, take a pencil and you put a pencil inside the glass of water, you will see that the pencil will sort of slightly bend. That's because of refraction, which is happening. And the atmosphere is sort of similar. It refracts light, so you see the apparent position of the star, wherever that would be coming from, it will change. That's fine. But the stars have always been there, so it's not like our. So as I sort of understood it, I mean, we're getting light from the stars, and the countability of, okay, you can count stars. There is not a problem that you cannot count, and for that you need to resolve them. You need to you have a telescope or something like that. You set it up and you just count all the number of point sources which you are getting, and each of them are having different locations where they are coming from. You can count them up. This was also done, for example, by a recent survey. It's called the Gaia satellite, and they counted all the stars. I mean, took data of all the stars in our own galaxy, the Milky Way. So they are countable. They're not countable. They're not infinite. And of course, and also if they were infinite, your sky at night, during night sky, would be as bright as the day sky, because you will have star at every position wherever your line of sight goes. So it would be bright as day, and we don't see it as bright as day. Tells you that they are not really infinite. So I hope that sort of answers your question about countability and also about what happens with refraction. So I'm going to take a question from I don't know. So let's say Kaustubh, are you there? Kaustubh?
Yes, sir. Yes, sir. Sir, I wanted to ask a question to Tarun, sir. Is he there
Okay.
right now?
Yeah, I'm here.
Yeah,
Yes.
Tarun.
Yes, sir. So, previously in your lecture, you said that if we are in a room and if sound was to pass to the next room, then it passes through the door. So suppose if this door is made up of lead, which restricts any ray to pass through it, will the sound ray still pass this door or not?
No, okay. So there are two things. One thing that you should imagine, you should distinguish between a few different things. Okay. Imagine that I'm standing here, you are standing in front of me. I don't know, let's say 10 meters away, and there's a wall in between. Okay. Now there are various situations. If this wall were in very very big, okay, that it extends very large in both directions. Okay. Then of course my voice will not reach you. That this wave which is created by me speaking, the sound wave would not be able to reach you. But that's not the situation that we were that I was thinking about or saying when I was saying earlier. What I was meaning is that imagine that this is finite in size. Okay, you are and we don't have a direct line of connection to each other. Okay, the claim is that when you speak, okay, you in such a situation when the wall is finite, okay, then you can hear me. Okay, now that happens with waves, but that does not happen with a ball. I can't throw a ball to you, right? I can't throw a particle to you without actually making a hole in the wall. Okay, of course I'm for now neglecting gravity. Of course you can throw it over the wall, okay, but that's the effect of gravity. Okay, so neglect gravity. But this is the crucial difference between particles. Particles, if they're not acted upon by some force, they just keep moving in a straight line. So if I throw the ball, it will either come back to me by colliding with the wall, or if I throw it on the side, it will just keep going to the side. You will never get it. Okay, but that's not the case with waves. Okay, when I speak, the waves generated, they reach you around the wall.
So I'll take one last question. I think then we can end the session. Okay. So I'm going to take this session, the question from Arpan. Arpan Basu, are you there? Yeah.
Sir, I'm Hemakshi of class 12 KV Kadapa. I would like to thank first of all Abhishek sir for the topic of a building block of water. And I'm asking a simple question that the difference between the microscope and LHC, sir.
Yes, Abhishek, we can hear you.
Yes. So you are asking the difference between a microscope and a LHC, right? So very simply, if I were to try and simplify it, when you're looking at a microscope, right, it's always you have some kind of electromagnetic wave, right, which is probing matter. So you are using the fact that there is some kind of an interference or a diffraction pattern which you may see because of scattering of that light with the thing which you're trying to see. Okay, that's probably the most simplified description of a microscope that I can give. For the LHC, what happens is that you have two particles which are coming in. They're basically a collision which is happening. So it's also a kind of an interaction, right? And then in this collision, you are putting in a lot of energy, right? The fact that we have a lot of energy means that you can probe a very small regions of space. Now, why do I say that? Now, if you go back to Tarun's talk, Tarun said something called as an uncertainty principle, right? Which basically means E into X is equal to a constant. Okay. Now, if E becomes very, very large, means that you can see X, which is very, very small, right? Because X is equal to 1 by E. Okay, so the LHC works on the phenomena that we have two protons which are colliding. It's producing particles which are are really small because of the fact that we are putting in a lot of energy into the system. The fact that we are putting that much energy into the system, by conservation of energy, you can create a particle which can be fairly heavy, right? I think I lost are you there?
Yeah, we're there. Yeah, we can hear you. Yes.
So the fact that we are putting in so much energy into the system, the more the amount of energy you are putting, the heavier the particles you can create. And the heaviness of the particle is related to the fact that you are seeing really small regions of space.
Yeah, that really puts it well. So I think we can we can close the session. We've already gotten to 12:46, right? So, yeah, I'm sure there are a lot of questions which would be unanswered, but that's a good thing that you have questions. So now you can look for their answers at the okay. So, so yeah, igniting questions is another useful and good task. So, is Somik, are you there?
Yeah, we can just conclude. Yeah.
Okay. Yeah, sure. So I'd like to thank the IIT Delhi Sci-Tech team members for organizing these two very excellent sessions. I hope everyone had really fun time going through this excellent journey with all of us. I'd also like to thank my colleagues, Professor Tarun and Professor Abhishek. This was excellent. This was an excellent introduction to the microscopics of our universe.